So our first speaker this morning is Rob Flack again, who's going to tell us about the life and work of Basil Hiley. Rob?
Cheers. Hi. Okay, so the first thing to note that Basil was actually was born in 1935, which, to set the scene for those of you who are not too familiar with the history of that period, because the British Empire was still was still operating at a level, and so Basil's father was a major in the Indian Army, and prior to World War II, and this is him here with his sister, and obviously their servants, and he was actually born not in India. He was actually born in what we now call Myanmar. It used to be called Burma in those days. He was obviously born in 1935 in a village or town called Yangon. They moved into India as the war progressed, because, as you know, the Japanese Imperial Army invaded Burma, as it was then, and eventually everything moved into India. In fact, actually, that is where the invasion by Japan actually stopped. It was actually on the border with India. There was a huge battle fought there at a place called Kohima, and that was where the war kind of started to, and that's where everything started to retreat from there. So he was caught up in that. But one of the activities he used to tell me that he'd love to get up to when he was in India was flying kites. And I hadn't known about this before talking to him, and I looked it up. And they actually have kite fighting. I don't know if very many of you are aware of that. And they actually, with the string for the kite, they actually get crushed glass, and they cover it with rice glue and then embed this crushed glass. And so they saw at each other the strings. I mean, it's quite remarkable, really. But he was into that quite a lot with his servant. He used to tell me, which is a bit there you go. But never mind, it's true. There's no point in hiding from it. And of course, India got its independence in 1947, and so therefore Basil's family then returned to England. Now, just a wartime story. Prior to the war in Europe, Basil's mum decided to bring the children back to England for a visit, for an extended visit, because it didn't fly very far in those days. Remember, it was all done by ship. So when you came back, you stayed for a year or something. You stayed for a long time. Anyway, but once the war got going in 1939, his mum decided actually maybe we'd be better off back in India. So anyway, but the last convoy going to India at that point in 1940, this is April 1940, was actually from Marseille, because obviously it was zipped down the Mediterranean, through the Red Sea, into the Indian Ocean and back to India. So he had to get back, so they had to get to Marseille. And this is in April, I think it's April 1940. Now, I'll put a map up here just to indicate. Around this time, is this working? Okay. Around this time, the German army was entering here. And there is Calais, there, where obviously you go across from England to Calais, and you get the train to Paris, and then the train from Paris down to Marseille. And that was his mum was whisking him across France about a month before the German army entered France properly. So in fact, it was a fairly close run thing that they got back to India on time at all. So, but obviously they couldn't escape the war entirely, because eventually back in Myanmar, the Japanese army invaded in 1942. So he was really caught up. Even at a very young age, he got quite caught up in the war in this way. And but then everybody of that generation did. I know my parents fought in the Second World War, so therefore, it was common. It wasn't uncommon, should we say? Right. So his education in India, because of this moving around, it didn't really settle down until he got back to the UK. And there he attended a college, which I think it still exists, Brockenhurst County High School. all right, from 1948 to 54. Now, this town is actually, I don't know if you know the geography of Britain, it's actually on the south coast, or near the south coast, and there's a town near Bournemouth and Southampton, which is, of course, where the ships go out. I've sailed out of there myself before now. But also, he had his favourite pastime, right after he stopped killing kites, his favourite pastime was actually football. And then he became an undergraduate at King's College London, and then he received his BSc in 1959. I think I've got my dates. I was in discussion with a couple of guys, and some of these dates could slip by a year. So if I do that, then I apologise. And then he remained at King's. He did his PhD there in theoretical physics under Professor Bohm, and then he received his PhD later in about 1962, 61, 62. Okay, so, and this is just a selection of pictures. Basil and Sylvia getting married, obviously, parents, etc. And that's Sylvia there. She died. She preceded Basil by about 6 years, as I recall, which was also a shock to us because I knew him at the time. Oh, come in. But anyway, that's his two children. Sally being the one in no, Sally's the oldest actually. I get it mixed up. Anyway, and then obviously I think he's only got one grandchild. We did have. So he led quite a varied life. He loved football. You know, I think if he could have been a professional footballer, he was pretty good apparently, then I think he probably would have done it. But obviously it's a different world. But in fact, not only did he play at school and he played also at university, but eventually he actually became a qualified referee and actually refereed matches up to a certain level. So it, shows a certain level of commitment to the sport. But there he is, captain of the school team. I gather from the date 54, 55 on that ball that it must have been probably his last year at school. Now, Basil followed Bournemouth. They're actually called AFC Bournemouth, Association Football Club Bournemouth, when he returned from India. And Bournemouth eventually was quite a small club in those days, right? But it rose up the leagues and now plays in the English Premier League. So it's in the big time. And on the day of his death, right, they played a team called Nottingham Forest and they won 5-0. And I am convinced that he died at the end of the match, that he got a bit excited and his poor old heart gave out. So, Basil and David, where did they meet? This is Cumberland Lodge. It was actually, it's a Grade 2 listed building in Windsor Park. Now, Windsor Great Park is where, obviously, in Windsor, this is where the king lives, at Windsor Castle. And so it's all part of this huge estate. And in fact, bits of it were given away in the end, 1659. I don't know how many of you are aware we had a civil war then, and the royals lost, and the Parliament forces, as they were called, the Parliament Army won, and Captain John Byfield was given this land, and he built this house. So, but anyway, since then, moving on 400 years, it's now it's held in a trust. And it's used for what is called educational purposes with special focus on young people. So the universities in London actually use it. They're not the only users, but they do use it. And in fact, the University of London hold a meeting there every year. Anyway, this particular year, I think it was 61. So it was obviously, I guess, when David must have left here and gone back to London. Well, not gone back, sorry, gone to London. And he was invited to give a talk on sort of this new quantum mechanics, as it were, at Cumberland Lodge to all the young students, all the youngsters. Anyway, which he did, and Basil was in the audience. and Basil he told me, he said how he obviously grew up on the Bohr and Born and all the usual stuff that we all learn as undergraduates, but he was really struck by David and his view, and so he really wanted to work with him. And as luck would have it, there was a position came up at Birkbeck, but interestingly, it was as an experimentalist, which is quite funny because he's totally useless in the lab. All right, and I have from first-hand experience. I'm not, so, but anyway, that was the way it was. Anyway, he got the job, obviously, and then he worked with David then right up till, David's death and then beyond. Okay, so this is where traveling with Basil, which I did several times. We went over this particular time was going to Sweden. I don't know how many of you know Maurice de Gossel. He's in Vienna. He's actually French, but he's in Vienna, mathematician. And Basil and he have published together, and they work very closely together. But it was like traveling with an errant grandfather at times, because the flight would be called. You're sitting there, flight's called, you think, okay, great. And you turn around and Basil's disappeared. And I'd have to go looking for him. Fortunately, I had a mother-in-law like that as well. So in fact, I knew exactly where to go. So, but eventually you'd find him and drag him off to the place. But he did love to tell everybody who even barely asked about what he did. And he loved telling everyone about quantum mechanics. And when we left, it was actually when his photographs out, we left the hotel here, and it was Basil and me, we had our own car going back to Gothenburg Airport. And I think it was about an hour's drive. It's quite a long drive anyway. And the taxi driver, like all taxi drivers all over the world, they all go, oh, what do you do? And I just thought, oh no, don't ask this question. And so and they obviously, they're always looking to get a bit of a tip, aren't they, at the end, being polite and all the rest of it. And of course, this poor man suddenly got the full implicate order, followed by a heavy dose of hollow movement. And I kept saying to him, Basil, I'm not sure he's that interested. Oh, I'm sure he's interested. I don't think he is. But anyway, I fell asleep. So, which is actually my answer to everything in life is, when in doubt, fall asleep. So, and then the older I get, of course, the easier that becomes. Okay, so Basil and David worked together, and they researched this deeper philosophical nature of quantum mechanics. They published a lot. We're all aware of it. And obviously, the undivided universe is probably maybe it's the pinnacle of their collaboration. But obviously, it came to an abrupt halt with David's passing in 1992. Basil tells me the story actually that the final proofs of the book, David was in hospital at the time, and he visited David, and David was reading them in the bed, as it were. And Basil visited him and said, are you happy with that? And he said, yes, I'm happy with this. And he kind of metaphorically signed it off, as it were, at that point. And that's so, but obviously David was quite ill at the time, and sadly, he died eventually. I don't know where this meeting is. If anybody could tell me, I'd be very happy to know. But in fact, he did rub shoulders with all the you can see Basil there, and I've circled in red, but he's sitting next to John Bell, and there's Vigna there, Despaignard and Josh, and I'm sure there are others, but my facial recognition software didn't work terribly well, but I'm sure. So if anybody does happen to know where that meeting took place, not now, but offline, if you could let me know, that'd be great. So this was Basil when he was 80, so that's roughly 10 years ago, just over 9 years ago. Basil, I organised a conference, like a symposium for him to mark his 80th birthday. And I was fortunate enough to be able to get Roger. And because Roger, as you know, Basil, David and Roger were at Birkbeck at the same time, which is massive sort of synergy, if that's the right word. And they used to, once a week, roughly, I think someone's already alluded, I think Chris Dewdney alluded to the fact that we still have this quaint tradition in England about afternoon tea, and that's when everyone grouped together. But they used to have regular meetings, and they would discuss quantum mechanics. And we're talking back in the 60s, so we're talking about the really early days. As far as I'm concerned, anyway, I was still a little boy then, so I was still running around shooting people with my little pop gun, you know. So anyway, so the other person in this group here, other than this this ugly boy on the end, is actually Chris Dewdney in there. He's standing between Roger and Basil. And I think that's for me, that's one of my favourite sort of photographs, actually. So I think it's when Basil was still, you know, physically, you know, still there. But it was after that, it's when he gradually started to decline. Anyway, there we go. And Chris will be doing his talk a bit later, showing these plots of the quantum potential of the sun, the animations, hopefully. I mean, they are brilliant. I've seen the latest ones, and they're really superb. So I think hopefully that'll be okay. Right. He also took part in lots of discussions he placed in Canada and places like that, but one of them was the BBC in 1999. And the discussion, part of the discussion, was an artist called Anthony Gormley, who's very famous for very large sculptures made out of iron. Right. I don't know if any of you are familiar with a sculpture is called the Angel of the North. And in Britain, that's if you go up north, up the A1, past Newcastle, the Angel of the North is there. But after this discussion, Anthony went away and created this sculpture, which still sits there on the River Thames. So if you ever go to London and you go down the River Thames, it's still there. And he called it Quantum Cloud. And he felt that this was, and obviously you can see it's a human being emerging from this apparent chaotic background. And this was a favourite phrase of Basil, was that there was this activity or process in nature which gave rise to quantum mechanics and so on. Okay, I love that statue, by the way. Oh, sorry, that sculpture is one of my favourites, I have to say. So, just as a personal view, the time that I was working with him, his real main thread was about quantum gravity. And he felt that there was some activity behind it, but his main thing was to actually try and find a geometry. And he settled on dealing with quantum, this sort of concept, this algebraic geometry, or geometric algebra. And so Basil's approach was to try and find this overall geometry, if he could, that would encompass everything that we already know. So taking inspiration from Dirac, Basil wanted to use an algebraic approach. He wanted to extend this into the realm of geometry. And as a starting point, he used Clifford algebras, which probably some of you already are familiar with. These were published, I think it was around 1870. Now, coincidentally, Clifford happened to be a professor of mathematics at UCL. It's not prejudice, but it's just a coincidence that is true. But Clifford noted that he himself took inspiration from the work of Grassmann. So this geometric algebra is extensively used in the computing industry, which was news to me a few years ago when I found out, and also robotics and games and so on. Because apparently it's a good way of programming in rotations, and it's the sort of easiest way with, because Clifford algebras give you quaternions quite naturally, and that's what they use. So just a quick note, Clifford algebra. Now I'll put this little quote up because I think it shows you this guy how insightful he was, because he says here, and I'll paraphrase, but basically you can read it for yourself. But basically what he's saying is that the geometry that he was using at the time, this sort of, the geometry which we all familiar with, the solid geometry, which inspired all their experiments at the time. But he did start to wonder whether, in fact, it was valid at what he calls small portions of space. And I think that was quite intuitive, because he kept saying, he wondered whether, in fact, if you went smaller and smaller and smaller, does the geometry change? And I thought that was quite insightful, bearing in mind around the 1870s. Well, he died in 79, so it must have been around that time. But what Basil came up with, well, not come up with, but what he used to promote was this tower of relationships, where he would list all the various algebras that are being used. And he noted that, in fact, that all the relationships that are in those, that there is obviously a pattern there, I think. And I think even as a non-mathematician, I can see that pattern. I mean, mathematicians hopefully can see it much better than me. But you can see this common thread running through them all. And that's what he was using to try and sort of get them, try and get them all together, as it were. Now then, I want to finish on a personal note. Basil began his journey with David, and one of the thoughts was that quantum mechanics, at its core, is a theory based on process and activity. Now then, I don't believe, this is just a personal thing, I don't believe that geometric algebra approach is sufficient to describe activity. And as evidence for this, because I come from a particle physics background, I don't know how many of you know this, but the Large Hadron Collider is known for two things. Firstly, finding the Higgs, but also not finding supersymmetry. But in fact, one of the other things that come out, I don't know how well known this is, but I've drawn this. These pictures are straight off Wikipedia, so but it's the artwork tells you. When I first started as an undergraduate, we could barely see that there was 3 objects in a proton, and it was obvious to make the connection to the theories of 3 quarks. Now, as it went on, we then realized that there was more going on than just quarks. And there was what we call a quark C. Now, when I was doing, later on, doing as postgrad, postdoctorate, and so on, we thought there was roughly a 50-50 relationship between the valence quarks and the quark C. The latest results of LAC actually pushes that relationship more in favor of the quark C. So it would appear to me that nature puts a lot of emphasis on the quark C, not just the protons. And obviously that all has to be constrained, because we know the protons won't decay. So in other words, this whole activity that's going on, and I asked the question, and this is just a general question, I'm going to end on this, and maybe anybody want to discuss it later, I'm more than happy. I asked this question: why has nature chosen this way to construct a proton? If I gave you all a bare blank sheet of paper and said, design me a proton without knowing all this, I bet none of us would come up with this. And yet nature finds this. And don't forget, the neutron is very similar, of course. So you and I, sitting here, are doing this. I hope, no wonder you all feel a bit iffy at times, because your protons and neutrons are going completely nuts. No, they're very active. And I then, from this, I say to Basil, look, we can't ignore this. Right, we have to, because this is, this is real stuff. And I then said to him, if we go below the scale, and the scale of this sort of a proton is about 10 to the minus 15 meters, roughly. If you go below that, and this is just that last question, last thought. I was talking to somebody here earlier, but if you take the Planck length as some kind of limit of 10 to the minus 34, you've got nearly 20 orders of magnitude in between. There is plenty of space for something to be going on, what I would call activity, right? I have no idea what it is, by the way. I'm not pretending I'm some kind of, I actually know what it is, but I think if we're going to solve this problem, this is just my personal thought, then that is where we have to look. And we need a better microscope, which does not mean a bigger accelerator. As I was joking to others around, the FCC a good friend of mine, a professor at UCL, called it the future comedy collider because, I'm sorry, I'm being a bit naughty now, but the civil engineering alone would cost a bloody fortune. And there is no, I can't see it happening. Well, it won't happen in my lifetime. In fact, I would dare say it wouldn't happen in the lifetime of anybody in this room, because it's going to take decades to, even if they got it off the ground. So therefore, we need to find, and this is really where my journey started, saying, forget high activity, high energy. Let's go look for low energy solutions to this. And you saw yesterday my sort of first foray into that. And that's where that's where I'm personally headed. Okay. Thank you. Thank you.
Thank you, Rob. Very interesting, fascinating tribute. Unfortunately, we don't have time for questions. We do need to go on. And our next presenter will be remote. So, there he is. Great. This is Roderich Tumulka joining us from Tübingen, who's going to give us a tribute to Detlef Dürer. So I leave it to you.
Thank you very much. Give me a second to open my slides here. Okay. And okay, I hope you can see my slides now. If not, please complain. I'd like to thank the organizers for their invitation, their suggestion to give a brief presentation remembering Detlef Dürer. Detlef Dürer passed away in 2021 at the age of 69 after short and serious illness. He was a leading researcher in the field of foundations of quantum mechanics, especially in Bohmian mechanics. He had actually coined the name Bohmian mechanics in analogy to Newtonian mechanics around 1990. Since 1989, Detlef had been a professor in the Math Institute of Ludwig Maximilians University in Munich, Germany, where he supervised a large number of thesis students on all levels, on the bachelor, master, doctoral level, including myself. I was one of his PhD students. Detlef is known for his book on Bohmian mechanics, which appeared in 2001 in German, and an English translation, revised and extended, co-authored by Stefan Teufel, appeared in 2009. Perhaps Detlef's most important paper was Quantum Equilibrium and the Origin of Absolute Uncertainty, which appeared in the Journal of Statistical Physics in 1992, written jointly with Shelley Goldstein and Nino Zanghi. In this paper, they explained how the Born rule probabilities for the outcomes of experiments by inhabitants in a Bohmian universe, a universe governed by the equations of Bohmian mechanics, arise from a Boltzmann-style typicality consideration of the initial configuration of the universe. And I see this as a major contribution to clarify Bohm's theory. Detlef is also fondly remembered for his kind personality and his sense of humor. His scientific work was grounded in the view that foundational questions in physics should be treated with the same high standards as other fields of physics. In this spirit, he was an outspoken critic of the Copenhagen interpretation of quantum mechanics. At the same time, he was not dogmatic about Bohmian mechanics. For example, he also co-authored papers about collapse theories, such as the Ghirardi-Rimini-Weber theory, and acknowledged that these theories would provide alternative possible explanations of quantum mechanics. In this photograph, I'm not completely sure when it was taken. So here, Nino, Detlef, Shelley, and myself were seen outside the physics building in Genova, where Nino is a professor. And Detlef was interested in many topics, in physics, math, and philosophy questions. Correspondingly, he had publications in physics, math, and philosophy journals. Together with Shelley, Nino, and his students, he studied many aspects of Bohmian mechanics, such as scattering theory, identical particles, particle creation, and the relativistic extension. But he also studied other topics outside of Bohmian mechanics or of quantum mechanics, including classical electromagnetism, statistical mechanics, electron-positron pair creation, and shape dynamics. To summarize, for his scientific creativity as well as his uplifting spirit, he is dearly missed by his collaborators and friends. Thank you.
Thank you, Roddy. I think we probably have time for a question or so, if anyone has anything they want to ask. Okay. All right. Well, thanks again for doing this, especially last minute. I really appreciate that very much.
Thank you.
Okay, the next speaker will be me. Can we get my talk up on the screen or? There it is. Okay, great. Yes. So this also will not be a very long tribute. So we'll make up for lost time. We'll be good. But I did want to mention at least Yves Coudet, who some of you know. So he was a experimentalist who's actually responsible for the image of this meeting. If you look closely, and it might look familiar, these are oil droplets that are being moved along by wave ripples on also a surface of oil. And Yves Coudet came up with these experiments. He actually once confessed to me he discovered them completely by accident. But he recognized sort of the potential and the interesting features of this type of system. And yeah, got a lot of attention for doing these sort of obviously completely classical macroscopic experiments that, from my interpretation, serve as a nice model, pedagogic model for pilot wave and guiding a particle and so forth. Anyway, learning a little bit more about him. So he passed away recently, well, relatively recently, sort of a bit before the pandemic, actually right around the time that Mahir Hussein passed away, whom we'll discuss next. But learning a bit more about him, he turns out to be have been a very interdisciplinary researcher who had a real gift for finding connections in different fields. He started out in solid state physics and then wound up doing fluid dynamics for most of his career. But again, kind of seeing the connections, things that other people probably would have noticed who are maybe more narrowly focused on their disciplinary silos, was really his great talent. And he also was apparently instrumental in setting up the materials center in Paris and became a member of the French Academy of Sciences and won this 2012 Euromech Fluid Mechanics Prize. So all in all, the kind of thinker and person who I think dovetails with the themes of this meeting for sure. And here's a little bit more on the walking oil droplets. The first paper on this work was published in 2005, but there were many more to follow. And at this 2013 meeting in Vienna, Foundations meeting that a number of us were at, where I first met him, this work got an awful lot of attention. Those of you who were there will know what I'm talking about. Interestingly enough, both the particle and the wave in this case are made of silicon oil, the same material. But for reasons having to do with surface tension and chemical potentials, the droplet doesn't actually sink into the oil below it, but hovers on the surface. And it really does hover. There's actually a thin layer of air in between the droplet and the oil underneath. So that results in basically a complex kind of coupling situation and interesting dynamics. Of course, you know, in Bohmian mechanics, the particle famously doesn't influence the wave, only other direction. Here, it's, you know, it's a bit of both directions, I'm sure. So, but still a really nice kind of way to visualize what might be going on in terms of pilot waves and de Broglie-Bohm particles. All right, we'll move on to our next tribute. Also will not be too long. This is Mahir Hussein, who, unless you're from Brazil, this is a name that you probably are not familiar with. If you are from Brazil, you absolutely know who this person is. He was a beloved nuclear physicist here at Institute of Physics at USP. And I met him actually at a semi-classical trajectory meeting, essentially. So not really a Bohmian meeting in Dresden. And we just happened to be sitting next to each other at lunch. And I didn't know who he was at all. But he was just like a very personable guy and very interested and curious. Again, lots of passions, lots of different kind of disciplinary interests, foundational interests. And by the end of that lunch, he was totally sold on Bohmian mechanics. And he was like, oh, we should work together. We should, you know, and we wound up actually getting a grant together and working on his favorite sort of pet project, which is the inverse Fermi accelerator, a model that was originally proposed to model cosmic rays of all things. Anyway, so this is how somebody like me wound up working with nuclear physicists for the first time. And that's all I'm going to say about him. But Brett Carlson, who kind of took over that project after Mahir Hussein passed away, will come up and tell you a bit more about Mahir.
Thanks for the introduction, Bill. Wow. See, Hussein, I don't need slides yet. Hussein was born in 1944, passed away in 2019. He spent 10 years, over 10 years, fighting a cancer that actually really didn't kill him. It was the experimental drug that he took that the side effects that eventually took him down. Although he lived for over 10 years from a cancer that usually kills in about 5. So it was probably worth the effort. Let's see. Well, I met him in 1981 when I was working on my PhD. He spent a year at the University of Wisconsin, and we started working together. We published a couple of papers there, and he invited me here. I came and stayed. So this is a dapper Hussein from the early years, 1971. You can see there's a comment that he isn't really too interested in the new technology from Volkswagen. But I have to say that his last car was just like that. It was an old, beat-up Volkswagen Beetle with a seat that didn't really stay up, but he succeeded in driving whenever he needed to. Well, he did his bachelor's degree in Iraq, and then he went to the US where he did his PhD with Arthur Kerman. And then he met Brazilians there, Pisa, among others, who invited him to Brazil. He came to Brazil and became a professor here in 1972 and spent his career here, although he visited, as said here, a zillion different institutions around the world. He loved to travel. It was, I'd say, half the time you'd come here to visit him and he was someplace else because he really loved to travel. He loved meetings. He was a really outgoing person and really prolific. After he retired, he was a coordinator of the nuclear astrophysics group that they had here at the Institute for Advanced Studies. And he was affiliated also with Michigan State University with the National Superconducting Cyclotron Lab that studies exotic beams, exotic nuclear physics. He was a Guggenheim Fellow, had a Gutzwiller Fellow. He was a member of the Brazilian Academy of Sciences and the Third World Academy of Sciences. He wrote a lot. He was very prolific. He has at least 2 books, one on radioactive beams and another on scattering theory in general. And let's see. Just to give an idea of his publications, he has more than 340, 71 physical review letters. I remember one year he was really proud of himself that he succeeded in publishing 10 physical review letters of the same year, which is something, I don't know many other people who do that. I don't know if anybody else has done it, but I imagine there are. 10 physics reports, and he was interested in lots of things, principally nuclear theory, nuclear reaction theory. As Bill said, the laser-driven accelerators, random matrices and quantum. What didn't work for me, but I can tell you what's here. Random matrices and quantum chaos, which is one interest that he always had. We did some things with that. Bose-Einstein candidates, symmetry breaking of fundamental reactions. Basically, this was parity violation in low-energy nuclear reactions. Buckyball collisions, atom-atom collisions, condensates, and nuclear astrophysics. He liked to do anything. There were lots of things that caught his attention, and that's about it. He was a prolific researcher, not only in studying, not only in writing papers and publishing new things, but also in having lots of new ideas. And he's sorely missed here. Unfortunately, he passed away before COVID, but not in time, too early to have coordinated this conference as he wished to have done.
Thank you for mentioning that last bit. I forgot to mention. He was actually originally supposed to be my co-organizer for this meeting. So this meeting has been in the works for 7 years now. It's finally happening. All right, let's move on to the scientific part of the program, and I will turn things over to your session chair for the final session. You all know him and love him, Valdir. I won't even try to pronounce your last name.
Oh, thank you, Bill. So let's move on. And the first speaker in the morning will be Mordecai Waegell. I don't know if I pronounced it right. So please.
All right, I want to start by thanking the organizers for inviting me to speak at this conference. It's been really interesting so far. All right, so I changed the title of my talk a little bit from what's in the book. Because this is really a Bohmian conference, I kind of want to emphasize that what I'm doing is very similar to Bohmian mechanics, but it's really not Bohmian mechanics. It's working with Madelung fluids that are going to be in space-time. And we're going to just show some tricks that allow you to kind of go from the Bohmian picture into this localized Madelung picture. This step of the derivation is not really mandatory, but it's a nice way to see the connection. So that's why I put it in here. All right, so this is the basic issue. Bohmian mechanics describes reality using a wave function that lives in configuration space, and the trajectories of entangled particles are interdependent. You can't really describe the motion of one without knowing about the motion of the others. And we want to undo that if we can. So for entangled particles, if you just start with the standard Schrödinger equation, the universal wave function can be replaced by a set of independent single particle wave functions that all live in space-time. They each have their own local evolution, or at least I'm working on ways to give them their own local evolution. I think that can be done. I have to make certain assumptions to get this to work, and well, you'll see what they are. But we're going to end up with an ensemble of single particle wave functions. They're all going to be in space-time, and they each will have their own individual wave function. We're going to use the Madelung interpretation for each of those, so we're going to replace that wave function with a fluid, and the wave function will be a property of that whole fluid, but there will be many of those. And then we have fluid now, so there's all these different fluid particles. Each of them has their own world line, and we're going to end up with kind of a local many worlds picture. So this fluid is conserved in the same way that probability current is conserved, and this is going to be a collapse-free theory. So it will end up being a kind of many worlds theory. Partly it's many worlds because I have all these particles that have their own world lines, kind of each recording their own experience, and partly because of the way that they get grouped together and interact in these subgroups that I was talking about just a moment ago. So you'll see how that all comes out. And we're going to be able to get entanglement correlations using local wave functions that live at each event in spacetime. So we're not going to have a universal wave function in spacetime anymore. It's going to be gone. Sorry, in configuration space. That's going to be gone. We're going to have, instead, in spacetime, point-like local wave functions, each of which is only informed by information that comes from its past light cone. So we will have a completely Lorentz covariant causal structure in this theory. and everything will be obeying local causality. It obeys special relativity with no modification. Okay. And I guess this is also a point just to mention, the real story here is the story of these local wave functions. What I'm about to talk about, where I start with the standard configuration space Schrödinger equation, maybe it's kind of a red herring. Like I said, it's a way to kind of see the connection, but I don't want to give the impression that you have to derive this starting from the usual Schrödinger equation. Okay, but here's how that looks. So I take the standard Schrödinger equation for many particles. I'm going to assume the Hamiltonian has no interaction terms. So a Hamiltonian is just a sum of single particle Hamiltonians. And obviously I'm going to have to put the interactions back somehow, so I'll come to that, but just bear with me for a moment. And I'm going to assume that I have some general entangled wave function already. So this is some superposition of terms, they're orthogonal, and so the sum of those lambdas squared is 1. And now if I just plug in this general entangled state and this Hamiltonian into the Schrödinger equation, I can expand it out into this form right here. And if you look at the form on the bottom of the equation 3 here, you'll see that I end up with a bunch of single particle Schrödinger equations just multiplied by all the other wave functions, and I end up with that for each of the terms in my superposition that I had. So now, in order to satisfy the single particle or the standard Schrödinger equation for multiple particles, I just have to satisfy all of these individual single particle Schrödinger equations. And I want to point out here that this is a strong contrast with Bohmian mechanics, because if in Bohmian mechanics I have entangled particles, their trajectories affect each other. But this is, so far everything I'm doing here is just standard quantum theory, and it shows that as long as there's no coupling, even if they're already entangled, I can treat all of these fluids as evolving independently. The trajectories do not affect each other at all. And that's a significant difference from the way that we treat the stuff in Bohmian mechanics. Okay, so now we have these single particle wave functions. They're indexed by I, where that indexed the terms in the wave function, the orthogonal terms, and N, which index the different particles that we were talking about. And so I have this host of different wave functions. And each of these is now expressed in terms of just a single coordinate, a single configuration space coordinate, x1 or x2 or x3. But I don't have any terms that require me to deal with 2 of those coordinates or more at the same time. So I can just replace all of those coordinate space coordinates with a standard space-time coordinate, and just drop all of these single particle fluids that I have, or single particle wave functions so far, just directly into space-time. And again, I'm going to have to get the interactions back, so we'll come to that. But I have all these things that are basically all in space-time, and ostensibly, if they're just following equation 4, then they're not interacting with each other. I have individual sort of packets of these wave functions, and I'm going to immediately switch to the Madelung picture now and make them into fluids. But this is now the step where we're going to get back the interactions. So if all of the interactions that couple different systems are local in space-time, which I think there's good reason to think that they are, then we can just treat all the interactions as coupling unitaries between the states. So, and those coupling unitaries are going to be related to how we build up the local wave functions I was talking about before. And we can characterize all of this now as just boundary conditions in spacetime that connect fluids before an interaction to fluids after an interaction, where the interaction may create or destroy entanglement in spacetime. And we're going to get all of the information that was in our standard wave function now represented using these spacetime wave functions. Okay, so now I'm going to introduce the Madelung picture. So we're going to go to the iconal representation for each one of these. And you all are all very familiar with this, but I want to stress that now we're talking about a fluid. So there's not really a distinction between like the wave and the particle. The wave is just describing the whole fluid. The whole thing is there. I don't have a separate single particle that's being guided along. But I'm going to be able to characterize this using a density function and a velocity field. So we've seen this many times in this conference. So these are just the standard equations that Madelung derived and Bohm used later on. And so we get this funny quantum potential term. What is the wrong thing? Oh no, I guess this works. Sort of. Yeah, it's a little bit off. All right, this is pointing really in the wrong place. Okay, maybe I can just use the mouse cursor. Can you all see that? Yeah, okay. So just put this down. All right, so we get this quantum potential. You all know what this is. And so this is now describing the energy of the particles in this fluid, the individual particles in this fluid. So they have a classical Hamilton-Jacobi equation, and the only thing that sort of makes them non-classical is the addition of this new quantum potential term. And I didn't put all the I and N subscripts onto these equations, but it's implicit that these are all, these are all coming from this single term Schrödinger equation, or single term wave function plugged into the single particle Schrödinger equation, and then you get out these two equations. That's the real and imaginary part of the Schrödinger equation. So you get a continuity equation and this Hamilton-Jacobi equation. And this shows that the fluids with different I and N do not interact with each other except through these coupling unitaries that I'm going to describe. So I have that. I already said this when I was talking about the wave functions, but now I'm going to think about this as the fluids. This is going to be the ontology. I really have all of these fluids in space-time. The amount of the fluids is always conserved, so that there's no collapse. And what's going to happen when I have branching in the many world sense is that the fluids subdivide into different subgroups. Okay, so I know this is a lot of conceptual stuff, and I'm going to try to now give you some imagery to help make it a little bit clearer how this works. Well, sorry, I'll get there in just a second. So this is kind of just recapping stuff I've been saying. So for a given value of I, that's the term in the orthogonal term in the original wave function, and for a given N in the system, we have a fluid of equally real points in space-time. No one is privileged, so that's why we're really fundamentally different than Bohmian mechanics. And each one of these is, all of the ones that have the same indexes, they're all interacting via quantum potential. But if I've got other fluids with different indexes, they have their own quantum potential, and they're not really interacting with each other. So think of this as a fluid where the quantum potential is now kind of internal energy that the particles in the fluid are carrying, and it's a function of the density of the fluid. So the density of the fluid, sort of informs the energy surface on which the fluid moves. And so there's a constant feedback between these two things. As the fluid moves, it changes the quantum potential, and then that changes how the fluid moves. Okay, and then each of these fluid particles has its own distinct world line, and to make this a fully local theory, those world lines are going to be light-like or time-like. We're not going to have anything that moves faster than the speed of light. And that introduces some constraints, but I'm not really going to have time to talk about that in this talk. And yeah, we call these, we say that these are in the same world, so that there's, like I said, they're kind of two senses of worlds. They're the individual world lines, and those are really how we're going to characterize the Born rule. You're going to kind of do counting of how much of the fluid goes to one outcome or another. That's how you're going to get the Born rule. But if they have the same indexes, that means that they share this quantum potential, so they're all kind of interacting with each other, even though they're not at the same exact location. Right? But I do think the interaction is local, and it's a little bit of a challenge to get it out that way. And if I have time, I have slides in here that I think I'll get to, but you'll have to catch me on time, Valdir. Okay, I think I've already said this, and yeah, the Born rule is just going to come from the relative proportions. So if I have this fluid divide up into 1/3 and 2/3, then that's going to be the Born rule probability in the long run. If I repeat an experiment many times, then it'll be some finite time, but I'll over a large ensemble, I will have found the thing on the 1/3 side 1/3 of the time, and on the 2/3 side 2/3 of the time. So the Born rule emerged from this, but it's important to say that the Born rule is followed exactly by this fluid on each individual instance. We don't get to see it that way because we have to do some finite number of experiments, but the fluid subdivides exactly according to the Born rule whenever there's an interaction. Okay, so now we're going to really flesh out the interaction. So when two of these different systems interact, their fluid particles are going to meet up. The fluids are going to kind of coalesce in space, and this is something you'll see in the next slide, but I'm not going to talk about any kind of long-range interactions right now because it complicates things. You can do it, but you really need to talk about local interactions where the two systems only interact when they meet at an event. And so if I want to talk about the interaction between two charges, I have to now treat the field that propagates, like I have to treat the force carriers as a quantum system so that I can say, okay, something left one charge and then arrived at the other charge, and that's what a local interaction will happen. So I'm going to use kind of a dummy interaction here where things are sort of ballistic and they just don't interact at all until they're right in the same place, and then they interact. And that'll get the point across, and then you can think about how it generalizes. Okay, so one I think kind of interesting detail here is that whenever you have any kind of entangled state, you end up with a superposition of different terms, which are just different ways where some conservation law can be obeyed. It's really obvious in spontaneous parametric down conversion, but it's less obvious when you're talking about entangling superconducting qubits that that's the case. But I think all entanglement is of that nature, that it's always just some superposition of different ways that you can have, like in a singlet state, for example, different ways that you can have spin zero. Okay. So now I'm going to define these local wave functions. And like I said, the stuff I did earlier wasn't really mandatory. This is really the fundamental thing that the theory is made of. I have these local wave functions, and I have this set of local unitary operators that are in space-time. And to define the local wave function at some event, I'm going to take the past light cone of that event. I'm going to bound it at some point by local states that were there along that boundary. And then I have a bunch of interaction unitaries that are peppered through space-time within that past light cone. And I'm just going to take that initial state and act all of those unitaries on it. And that's going to give me the state of the local state that lives right at the tip of that light cone. And so that's how I'm going to define all of the local states that appear in this. And it's important to understand that this is just a local piece of information that lives at that point in space-time. So even if this is an entangled wave function, it's not describing any kind of connection between things that are space-time separated. It's more like a record that just lives at this one spot. But that record is going to have a dynamical role in this theory. Okay, and so what's going to happen is that, I said we were going to replace the wave function by this ensemble of wave functions indexed by I and n, but now something is going to happen even to that. It's going to become piecewise, because I'm going to have branching occurring as a local thing in space-time. So like a fluid can go in, and then because of an interaction with their system, branch into more fluids. And that means that when I'm describing one system, I might have some number of fluids on one side of the interaction and a different number on the other side of the interaction. So I'm going to have this kind of messy piecewise ensemble of single particle wave functions. Okay, and now let's actually really see kind of concretely how this works. So this is just a von Neumann measurement, or part of it. We don't have a collapse here. And this is my idealized interaction. So I have two wave packets that move along. They're carrying spins, and then there's going to be a spin-only interaction, and it only happens locally when these things exactly meet. So there's not any kind of long-range, spin-spin interaction here at all. And it's a big idealization, but it just allows you to see the fundamental thing in the simplest possible way. Okay, so I have this is my pointer state here. It's coming in, and I have some arbitrary superposition for a spin state or a qubit state. This is, the A and B actually correspond to, the mod square of the A and B corresponds to the actual amount of fluid, and it's arbitrary, but I've drawn it here so that they're equal. So this drawing is as though A1 and B1 both mod square half. But in general, these could be any values, and the density of the fluid, will be affected by that. So I'll show an example in a little while where that's clear. Okay, so what's happening here is that I have my initial states for these two systems, the pointer and the system I'm going to measure. And now, once they start to overlap, we're going to have kind of one-to-one interactions between the fluid particles. And you have to do it in this one-to-one way so that right at the event where they're interacting, I can tell the fluid to divide in the right fractions, because I have to have an equal amount of, I have to have A1 matching for these two systems when they come out, because that's how I'm going to get something that's consistent with a standard entangled wave function. So I'm going to have, when the fluids meet, I'll have to, at each point as they're intersecting each other, I'll have to subdivide them into 1/3 and 2/3, and I have to do it for both, so that I end up with a correlated term for system 1 that has 1/3 of the fluid, and an equal amount of the fluid of system 2. Because when I start with a standard entangled wave function, I've got a sum of terms that have coefficients that connect product states of all the different systems that are involved. So the coefficients kind of mean that the amount of fluid in each of the terms indexed by I has to be the same for all the systems. Okay, so this is trying to show the process dynamically, and so we can really just characterize the unitary as being a boundary condition. It's just coupling the fluid, for the pointer state. As this is happening, this is a dynamical process, and this unitary is telling me how to couple the dynamics of this packet on this side to these two packets that are emerging on the other side. And so you can see the piecewise nature of the wave function emerging here. I go from having one fluid for the pointer system to now having two different fluids, two different orthogonal terms. And to see what the wave functions are doing, when this interaction occurs, I go from this product state of these two initial states, the ready state for the pointer and whatever the initial state for the other qubit was. And then I do the unitary, and now I have this entangled state. This is the local state that appears right here, because now both of these initial states are within the past light cone, and this unitary is a local thing that kind of lives right here. And so the local state is, becomes this state. So this is what's happening as the fluid crosses this boundary. It's undergoing a transition from this, and that's happening in a continuous dynamical way in space-time. Okay. So now we have to see how you can deal with entanglement, obviously. In fact, this was what led me to this whole program in the first place, was thinking about Bell correlations. A lot of this work actually was inspired by the work of David Deutsch and Patrick Hayden, 1995 paper, where they introduce a way to deal with quantum mechanics locally in a many worlds type of picture, but they did it in the local Heisenberg picture and only really for qubits. And most people haven't really been able to make any sense of it. And so what I'm talking about here is kind of like the local Schrödinger equivalent of what they did. Okay, so I'm going to use the Wigner-Merman-Bell test. I hope everyone knows what that is. I'll quickly review it here. So you prepare a singlet state. You send one particle off to Alice and one to Bob. Each of them is going to measure one of the directions, one of these three directions here. They're going to choose them freely at random, or freely, maybe not randomly. And then there's a Bell inequality. This experiment violates, which I'm not going to derive. Okay, and then due to the symmetry of this experiment, I only actually have to look at two cases in detail. The case where they both measure the same direction, and the case where they measure two different directions from this set. And if I can just rotate the basis so that those two cases will cover every possible case here. Okay, so let's look at the case first where they measure the same setting. Can people see this? I was not expecting the screens to be so small. So I'm hoping this is really actually visible. If you can't see it, maybe try to find a TV you can move a little bit closer to. Okay, so we start with our singlet state down here, and we have a ready state for Alice, and we have a ready state for Bob. The source prepares the singlet state, and this gets sent off. This is microscopic, and so the choice of preferred basis, I've drawn this in, is completely arbitrary. You can think of this as having any preferred basis. And so for microscopic systems, the division between these fluid packets is not really enforced in any way. You can recast it in any basis you want, and the calculation will always work out. But once you have macroscopic observations, then you definitely have a preferred basis. And so once we get up to after Alice and Bob have measured, then we definitely have clear separation for Alice and Bob where they've seen spin up and spin down. Okay, so we start off here. We come to this interaction. This is where Alice measures. She does a unitary on a qubit, and that unitary causes the local state here. Because if we go to this point right here, now we just have this thing in our past light cone, and we have this in our past light cone. And so this is the local state that we get right here. And you see it's an entangled state of Alice and qubit 1 and qubit 2, but Bob is not involved in any way because he's not in the past light cone at this point. His interaction is not, anyway. And on the other side, it's symmetric. We get, I skipped a slide, sorry. I was wondering why that changed. Okay, so back on this original slide. So on what happens on Bob's side is symmetric. We get an entangled wave function of qubit 1 and qubit 2 and Bob, but Alice is not involved in any way. And this is a many worlds theory. There's no collapse. So when this happens, Alice's fluid divides into two different fluids. So now we have our two copies of Alice. I'm representing Alice here by a single particle, which is also an approximation, but again, it gets the point across. It doesn't really change anything if you try to treat her as a more complicated system. You can just think of this as her pointer, and then she looks at her pointer and becomes split up in the same way, her pointer device. So if you look at the terms here, it's kind of a funny notation. This is Alice, and so I've given her kind of like the non-subscripted term here. So I've got a world where Alice saw 0 and a world where Alice saw 1, and the coefficients are 1/√2 minus 1/√2, but mod square, those are both half, and so I have equal division of the fluid, and that's why Alice sees probability 1/2 to get either outcome. And if you read the sum of these two terms here, and you pretend those subscripts are not subscripts, then you just get back the wave function that I wrote above. But really, you should think about this as kind of like a record. There's an Alice who saw the state 0, and that means that she encountered the spin in state 0. And so there's also the spin in state 0 and encountered an Alice who saw the spin in state 0. So these are matched up. That's the entanglement correlation. And likewise for 1. So now I have my two Alices, and again, this is symmetric over here. I have my two Bobs now. We have two Alices and two Bobs. They're all in space-time together. It's not really any sense in which I've obeyed an entanglement correlation yet. I haven't matched up an Alice who was up with a Bob who was down or anything like that. Okay. But now we're going to come to this point. Maybe Alice and Bob get together. Maybe they send signals to some common experimenter who's in the intersection of their future light cones. To make this as simple as possible, I just say the qubits just keep on going, and Alice just goes off and meets Bob at event C. And they already have macroscopic outcomes, so there's no additional unitary operator I have to include at C. It's just got to be the identity. But now, once I get to C, now I have all of this stuff. Both of their unitaries are in the past light cone of C. So now, by definition, the definition we're always using, I get this local wave function. I act both of the measurement unitaries on the initial states that I started with, and I get this full entangled state of Alice and Bob and qubit 1 and qubit 2. And now if I look at that local entangled wave function, you can see that I have an Alice who got 0 and a Bob who got 1. So that tells me how these get matched up. The Alice who saw 0 meets the Bob who saw 1. Those interact. The Alice who saw 1 meets the Bob who saw 0. Those interact. And the other two just don't see each other at all. And so now I have two pairs of Alices and Bobs, and both of them have seen the entanglement correlations being obeyed. And all of this was accomplished using, completely obeying local causality. I didn't have any connections between space-like separated things, and the trick of that was to wait until I get to the intersection of the future light cones to try and match them up in any way. So this delayed matching is really kind of the heart of the trick. This is how you can have a separable theory in space-time that obeys local causality. You can see from this entire diagram that this causal structure is Lorentz covariant. If I boost to another frame, maybe the measurements don't appear to be simultaneous anymore, but the details about when I have things in the past light cone does not change when I boost to another frame. That all stays the same. The local wave functions all stay the same, and so this works out in a completely Lorentz covariant way. Okay, so now let's look at the other measurement setting. It's a little bit more complicated, but it illustrates what I was talking about the different fluid densities. Sorry, this one I think is even smaller, so I apologize if people are having trouble reading it. Okay, so everything that happens for Alice is the same because she measures, everything that happens up to her measurement is the same because she still measures the 0, 1 basis. But now I have to make Bob measure one of the other bases, one of the other directions, and that's characterized by measuring this basis here, which I call phi plus and phi minus. And so when Bob measures that basis, what happens is that there end up being 4 outcomes, and they have different weights. So I have 3/8 of the fluid, Bob, I'm not sure if I used the right notation here. So I said Bob's detector settings still have the same outcomes. So if he sees up, it's a 0. If he sees down, it's a 1. But now him seeing 0 means he saw phi plus, and him seeing 1 means he saw phi minus. So sorry if the notation is a little bit confusing here, but that's what's going on. So I have these 4 outcomes, and so 3/8 of the fluid goes to an outcome where Bob saw 0, and that meant that the thing was in phi plus, I'm sorry, I think the way that I just explained this was misleading. That I've changed the basis, so if he was measuring in a basis where he only got 2 outcomes, it would be what I just said, that the 0 would correspond to phi plus and the 1 would correspond to phi minus. So I tried to do this so the readouts on his detector look the same as they do. He just rotated like some analyzer before it got to the detector. So anyway, this is the state that you get out if you apply this coupling unitary. It's the superposition of these 4 terms now, and I have 3/8 of the fluid going into a state like that, 1/8 going into a state like that, and oh no, I think I did say it right before. I'm sorry, I just confused myself for a moment. It only has to do with what's going on with the other qubit, the one he didn't measure. That's why there are 4 terms. So this state already had a record of what was going on with the first qubit, even though it's space-like separated. And so that's why each of these terms subdivides into 2 terms. So if Bob sees 0, he always sees phi plus, and if he sees 1, he always sees phi minus. But I have different records of what was going on with the first qubit from when it all happened, when they were back at this interaction. So again, I'm allowed to use this information here because my local wave function is constructed by taking this initial state and this initial state and acting this coupling unitary on them here, because this is all in the past light cone here. So now you can see the fluid doesn't always clearly divide into half as in all of my previous slides. It really does divide up meaningfully into different fractions, and that's where the Bohr rule is going to come from. And now when Alice and Bob meet, it's still the identity operation, but we get this state now because all of both of the measurements are now in the past light cone of that event, and so Alice subdivides again into these 4 worlds. So we now have 4 worlds for Alice and 4 worlds for Bob. And this is not, because they didn't measure parallel bases, the entanglement correlations are not perfect. You wouldn't expect them to be, but these are the correct entanglement correlations for those measurement settings. So this reproduces the Bell correlations exactly. We get we violate the Bell inequality. Everything works out the way it normally does. Okay, so this is kind of my talk is kind of weirdly ordered. I wanted to get to this because I think if you're going to claim you've got a local theory in spacetime, you have to do Bell's theorem. You have to explain how it's going to work, how you're going to get the correlations. But now I'm going to go back and talk a little bit more about the fluids. And how am I doing on time, Valdir? Okay. So I'm probably not going to be able to get through all of this. Okay, so this is now just really talking about the Madeline picture, where I'm going to think about each of these individual fluids and its own dynamics. So I'm going to treat the total potential energy of a particle in this fluid as the sum of its external potential. I called it V in an earlier slide, but U and Q, which is the quantum potential. And then it has a total kinetic energy, which we call K sub A. And that kinetic energy, the A, is going to stand for average, which I think I'll have time to explain. I don't think that the particles are moving. I don't think the grad S is the velocity of every particle. I think that it's the average velocity of the particles that are at a given location. Okay, so all the non-classical behaviors, tunneling, interference, those are all going to be explained by Q, though actually Angel made me question if that's actually exactly right. That seemed intuitive from the way the equations worked, but your classical Schrödinger equation thing, seemed like you were somehow still getting some of those effects, even though you've taken out the quantum potential. So I have to look at that more carefully. Okay, and then for energy eigenstates, the fluid is in equilibrium, so your kinetic energy is 0 everywhere. And what that means is that the sum of your two energies, the quantum potential and the external potential, has to be just E, your energy eigenvalue. So you have a flat surface, and the fluid's sitting there at rest. And because it's on a flat surface, it's in equilibrium, it doesn't move. And this is a little bit more satisfying to me than the usual Bohmian picture of an eigenstate, where you have just a particle sitting somewhere at rest, and then a wave that's stationary, but the particle sort of in some arbitrary position. Here, the whole fluid is participating in creating this quantum potential. And so the whole fluid has to have particular shapes in order for you to get this flat quantum potential plus external potential. And you can get back the time-independent Schrödinger equation from this, where you can see there's a particular discrete set of shapes you're allowed to have. Each one will have a different energy. Well, you can have degenerate cases too, but they'll have some energies, and they'll be flat at those levels. Okay, I think I kind of just said this. So yeah, the shape of the quantum potential is determined, the shape of the fluid is what's determining the quantum potential, and that's determining the experience. So that the force that the particles are experiencing. And so we have kind of a coupled evolution between these two things. I guess I said that earlier, before I was talking about the eigenstates. This is about dynamics now. Okay, and now I kind of want to give just a characterization of what it is the quantum potential does. Try to get a general intuition. So these are all cases where I have a superposition of the ground state and the first excited state in some kind of potential. And you can see what the actual potential is from the kind of the gray line. So this is an infinite square well here. And then I've got here a finite rectangular barrier in the middle, so it's kind of a double well. And then here I've got like a quartic double well potential over here. And here I've got a harmonic oscillator. And if you look at this superposition, this is superposition taken at exactly 1/4 of the period of the oscillation. So if I start at time 0, this superposition has most of the fluid on one side. But if I go to this T/4, it's right in the middle of tunneling through. It's tunneling in the sense that it sort of breathes back and forth between these two modes. And I'll show an animation of that. I'll interrupt my talk and show an animation of that, or maybe I'll have to stop there. I'm not sure how I'm going to end up on time. What I want you to see here is that for all of these different kinds of potential, what the quantum potential does is kind of just cancel out the shape of whatever the external potential was. So you get almost the same behavior in all the cases. You get the sum of the two energies, that's this blue curve, just ends up having some kind of a dip in the middle, and that's canceling out the barrier in the tunneling cases, and it's providing extra kinetic energy for the particle to flow through there. So there's something about the quantum potential that kind of tries to make the overall potential these particles are seeing kind of more uniform somehow. You can take up a lot of different kinds of scenarios and end up getting something that looks qualitatively almost the same. Okay, so I think what I'll do is interrupt my talk here to show an animation that I prepared that I could not easily include into my slideshow. So this is the dynamics of this happening for one of these cases. So you've got, this is the actual density because this is one-dimensional, and then I've also shown them with the vertical axis getting the energy, just like in the diagram, the animations I think Chris Dewdney will show later on. And so this is showing, and these again, I don't want to think about this as individual Bohm trajectories. I want to think about this as a whole fluid. And this is showing how the tunneling process works. So you can see this, the blue line is the sum of the quantum potential and the external potential. And the particles are essentially, falling into this hole, which is created, where the barrier should be. The barrier gets canceled out. This hole gets created instead. They fall in, and then they climb out the other side. And there's a little bit of other dynamics happening because the quantum potential is changing. And so, the energy, part of the way that the energy of these changes is as they rise up these hills, the hill is moving underneath them as well. Okay. All right, so so this is just showing half of the process. It starts at one side and tunnels across, and it's just going to repeat this and go all the way back, and then it just cycles. But yeah, I think this is just a really nice intuitive picture of what's going on. It gives you just basically classical equations of motion that are describing how this thing is tunneling. And the only thing you had to add was this quantum potential to get this total potential surface to behave like this. Okay. All right. How am I doing, Valdir? 5 minutes? Okay. I'll see if I can say a little bit more from my talk. If I can get back to where I was. It's Control Y, is that what you said? L. Okay, great. Oh, good. I'm on the same slide and everything. Okay. Okay, so now, why was I calling that velocity the average velocity? So I'm going to introduce this idea of the symmetric velocity. My slides are not in a good order, so I don't think I'm going to really get to explain this in detail, but this is the basic idea. When you look at the quantum momentum density for this fluid, it has a real part and an imaginary part. And the real part is the one we associate with the average velocity, grad s. The imaginary part is grad r over r, and that's the thing that sometimes has been called the osmotic velocity, but I'm going to call it the symmetric velocity. And the reason is I'm going to take the I on there to mean that there's a couple of reasons for this. One is that all of the motion of the fluid, the overall motion of the bulk, you see that from looking at grad s. So this grad r over r term, it's not contributing in any way to the bulk motion of the fluid. But I still think it's velocity. And to get that to make sense, it has to be that it's a part of the velocity, but you have a distribution at each point. And so you have the average velocity plus this extra osmotic part, but it's the distribution at one point has a sum of directions that sum to 0. So the average flow there is 0. It does not affect the bulk flow at all. And so this is the condition, the symmetry condition here, that I have all these different unit vectors r hat, and this is the magnitude of the velocity that I had from the osmotic velocity, and I just assign a direction to it such that all the directions at a given point will add up to 0. And that allows something really interesting. It lets me do this kind of interesting trick. So if this is the velocity, then when I if I were to write a classical kinetic energy, I would expect to have cross terms between these two velocities here, the VA and the VS. But because of this condition, those cross terms all cancel out. And so I'm able to just take the symmetric kinetic energy term and this original average kinetic energy term down here and combine them together into a single classical kinetic energy term, which is understood to be averaged over all the trajectories at a given point. Because I'm averaging over all the different directions the thing could be pointing for the symmetric part of the velocity. Okay. And so I can sort of recast this as that's the total kinetic energy. And I like that because the symmetric energy is the one that's not 0 in an eigenstate. When you're in just some stationary state, normally all the energy is in the quantum potential. Well, unless you have forbidden regions, it gets a little more complicated, but for like an infinite square well, it's all in the quantum potential. But when you go to this picture, it's all in the symmetric kinetic energy. And so it's always seemed more intuitively natural to think that when I have a bound state, if I had a bound orbiting state, it's in motion. And this is saying that, yeah, it is in motion, but it's a kind of motion where all the motions are such that they're all canceling out and not producing any bulk flow. So the symmetric energy allows the state to be stationary, but still in motion, this idea of the symmetric velocity. Okay, so to get this out, we introduced something called the reduced quantum potential. And again, I'm introducing this all in the wrong order. But this reduced quantum potential is a different object than the usual one. They're related. And it has a nice property that it's always, the integral of it over the whole fluid is always 0. So essentially you have this internal energy which can be borrowed from one part of the fluid and given to another, but you never get to add any amount that's above 0. And in the standard quantum potential, that's not the case because, again, in eigenstates, all the energy is quantum potential energy. Okay, so yeah, this is kind of what I was just saying. So I can, no, this is a little new. So the standard way we can think about the energy is just the sum of kinetic plus potential. And the usual way we can break that down as the kinetic of the average part plus the symmetric part plus this reduced quantum potential plus the external potential. And then I can combine these together. Oh, sorry, this is supposed to say KC over here. That's a typo. Oh, wait, no, I'm wrong, I'm sorry. Okay, so let me actually, I'm gonna run out of time, so let me actually get to where this comes from. So we have these two different pictures, one where you think about the total quantum potential and the average kinetic energy. That's the one that is more intuitive for looking at animations like the one I showed, where you see those nice surfaces. When you include the symmetric kinetic energy, it becomes less intuitive, but I think it's a more physical picture because it has motion in eigenstates and things like that. Okay, so yeah, this is talking about the quantum momentum density, defined in this way. This is the fluid momentum density, and this gets out the real and imaginary parts. This is how we define the two different kinetic energies I was talking about before. So they just come out of that operator. And for the energy density, it's the same way. And this is where we get this reduced quantum potential. So I just start with this right here as my kinetic energy density for the fluid. And now I have this quantum potential term, and I can just rewrite this in this way. It's the sum of this term here, which is positive, and this term over here, which is the reduced quantum potential. And you'll recognize that that term is the symmetric kinetic energy that I was working with before. And so I'm able to make this little trick, or do this little trick here. I can take the quantum kinetic energy density, which I would have originally talked about as standard quantum potential plus kinetic energy, and I can break the quantum potential up into these two terms, and then I can absorb this symmetric part into the overall classic kinetic energy. So that's how I get the two different pictures. So in one picture, I have a reduced quantum potential, classical kinetic energy. The other one, I have a standard quantum potential and the average kinetic energy. And they each kind of have their advantages. I think looking at them both can be useful. Okay, am I out of time? Okay, let me try to say one more thing really quick, because I think this is why I added a bunch of this stuff to my talk. I originally ended on that Bell's theorem stuff, and I think I wanted to get a little bit more into this. So I wanted to look at local energy conservation. So I have all these energy densities for the fluid, the kinetic, the various types of kinetic, and the various types of quantum potentials. And it occurred to me that I didn't know if those energies, if I'm thinking of them as true energy densities in the fluid, are locally conserved. So that's what I wanted to look at here. I wanted to look at the continuity equations for those energy densities. And what you find out is that it's not locally conserved on its own, naively. But if you add an extra velocity term here for the quantum potential to flow, not just being carried along by the particles, but to actually spread between them, kind of like heat diffusing in a pipe or something. It's kind of a bad analogy, but yeah, the energy can move from one particle to another. It doesn't have to just be carried along by them. Then you can find a velocity which then makes the energy to be locally conserved. So you have to add this other, you have to think of the quantum potential as a kind of energy that these particles have, but the whole fluid is there, and all of the particles in the fluid have some, and it can be carried along by them, but it can also be exchanged between them. And then you can get it so that all of the energy is locally conserved. Okay, and I have the details of how all the different types of energy couple to each other and how energy flows from potential to kinetic and quantum potential to kinetic and all of this. That's in the paper that, where all this is coming from. And you can do this for both the reduced quantum potential and the standard quantum potential. So whichever picture you're working in, there's a way to define the velocity. And you have this divergence-free field here. That's some arbitrary term that appears because of the way you derive this. Okay, so yeah, we have local energy exchanges. This is kind of what's going on. So these are the power density exchanges between the different types of terms. So you can see like the symmetric is exchanging with the reduced quantum potential, which is exchanging with the average kinetic energy, which is exchanging with the external. And then if you simplify down to these two pictures I was talking about, it works like this. But without adding that extra velocity term, there would be something wrong going on in the Q terms, both the reduced and the standard, where the energy would not be locally conserved. And the thing that's causing that it's an extra term having to do with the changing of the density. And so you need this, as the density is changing, the thing has to be able to transmit energy from one particle in the fluid to another to get it to balance out. Okay, that's the end. And I have bonus slides that I'm not going to get to. So, all right, so we have a locally causal separable theory of quantum mechanics. All the physics occurs in space-time. You have these local wave functions that are recording information, but it's only information about the past light cone. Yeah, it's a many worlds theory. And yeah, and this is obviously what I did here was using the Schrödinger equation and the Madelin equations, follow from that, even though a lot of what I was doing had to do with relativity. but that piece was not relativistic, and I think that we will be able to find good relativistic generalizations of that, and most of the intuition of what I've said here is going to carry through to the relativistic case, or that's the ambition anyway, so we'll see if that works out. And I just want to thank a lot of people. All of these people are deceased. There are a lot of living people I'd like to thank too, for their contributions that helped kind of guide me on my way towards thinking about the theory this way. And I don't think I need to name any of these people, though maybe I'll just point out Madelung. I think he's a little bit less known than everyone else, but yeah, you know who the rest of these people are. I think. All right, thank you very much.
Well, thank you for the talk, and I still have some time for questions.
Kai, excuse me for the same question. I still have no idea what fluid means. Sometimes you say a particle of a fluid, sometimes you say one particle fluid. Can you just define it as a theory of particles? Or fluid is something else? In Bohm, I understand there are particles and there are wave functions, which are kind of your fluid. But what is something number 3? What is fluid? I have no idea.
Yeah, so,
I couldn't understand it.
So if you understand kind of how the tables and chairs appear in Bohmian mechanics, they appear just the same way here. It's just that when you have these local interactions, you have a whole bunch of one-to-one interactions between the particles and the fluid. And so each time they're interacting, they're recording one of those outcome states that's allowing them to be divided into the right fractions. So you have many copies of the tables and chairs, but each of the things is always paired up one-to-one. So what you get back is just many copies of kind of the usual Bohmian picture. The fact that it's in space-time complicates it slightly, but it's intuitively not any different. So it's a many worlds theory of the type that you like. But so when I measure a particle position, I find it in one place. But there were a bunch of other copies that found it in other places. And if I look at each one of those, I'm going to get a reconstruction of kind of the world that we see. And they're just going to make many of those reconstructions. Did I answer your question? Still confused?
No. There are particles, and there is a wave function. This I understand. Fluid is something number 3, or fluid is a wave function. What is it?
Okay, I would say that ultimately I think that they're mathematically equivalent, but the ontology is that the fluid is what's there, and the wave function is just a mathematical description of it. That again, I got all these equations from the Schrödinger equation, at least in this particular way that of deriving it. So it's equivalent in that sense. Like, I mean, the Madelung equations are the Schrödinger equation. There's no actual difference between them. It's just a matter of interpretation. So what I think is, in this kind of picture, I think that the fluid is the thing that's real. The quantum potential is what's guiding its motion to some extent, along with interaction potentials. And that's kind of the whole story. So.
A really interesting talk. Thank you for that. I think there are some connections here with the things that we're doing in chemistry. I just really want to point that out. There's a lot of other things we can talk about offline, but I'll just say this for now. So for example, we heard about MCTDH in some of the chemistry talks. So that's basically using a tensor product form, which is the basis of what you have here. The interesting part to me is that that form is preserved with the type of interaction that you have. It's sort of designed to preserve that form. Whereas normally in chemistry, that wouldn't be the case. So I'm just like thinking out loud a bit here, but there might be some sort of numerical ramifications for us if we can find a way to kind of express our Hamiltonians in sort of your form, or even approximately, that might be a worthwhile thing for us to do.
Yes, I'm not familiar with that approach very much, but I was kind of thinking the same thing as I was listening to these talks. But I want to give a cautionary note here, is that I had to leave out any long-range interaction to get the picture to be this simple. If I put those long-range interactions in, I kind of think that you have like sort of the potential for couplings to be at every event in space-time also. And so you're going to have these fluids sort of subdividing constantly all the time. So I don't think this is going to be useful for doing computations, at least not as it stands. Maybe there's a way to kind of like simplify some part of it and get it to be practical.
Well, we don't mind approximations. Okay. So. And also you had something that's similar to another method that somebody talked about called multiple spawning, where the actual number of pieces can change.
Yeah, the number of pieces changes while preserving the amount of fluid. Yeah, we're just branching it out.
Okay, thanks.
Oh, we are running out of the time, but okay, one more question.
I'm happy to talk to all of you over the coffee break. So.
Yeah.
In the section of the talk where you were talking about Alice and Bob and so forth, does the quantum potential come in there at all? Because it wasn't clear to me.
Not really. I mean, the quantum potential is playing a role in how these fluids evolve, but I guess I didn't say this. The idea of this is that I have spatial wave functions, but the spatial wave functions and the spins never become entangled in this picture. The packets are just there to carry the things along to their local interaction where the spins interact. And so, yeah, I mean, these Gaussian packets do move along partly because the quantum potential is there helping them move along.
But you don't need that. It doesn't seem like an incident, like it's an integral part of this part of the.
No, it's not. Yeah. So explaining the entanglement correlations doesn't really have anything to do with that. But yeah, the reason that I focus on the quantum potential was the thing I tried to squeeze in at the very end about the local energy conservation. That I think that just saying that you have local packets, originally I thought that was going to be enough to give me full local causality. But then I ran into this problem with the energy density and had to add another fix to get it so that now even the fluids for the individual things are preserving energy locally as they propagate.
I'm sorry, we are running out of the time, so maybe we can, you can ask questions during the coffee break, please. And well, thank you very much for the talk. Yeah, please. So can you come back by 11? So we're still a little bit late, but we'll be okay. So by 11, okay? So before we start, so we have some few words from Eric Bittner, so please.
Okay, thanks. I just wanted to remind everybody that we have a submission portal for our articles on Philosophical Magazine. I don't really want to have any more than 3 or 4 minutes, not even 3 or 4 minutes, a minute and a half, seconds to talk about it, and that is we will be sending you a link with a submission portal right to the click here type thing. Like I said, we'll have peer-reviewed papers that I expect to be high quality because it's a high quality group, and I will be volunteering people from this group as referees, or at least one of the referees. So please do that. I would like if the world is perfect, I would be more than happy to have these in press in 2025. So that gives you a timeline for getting your paper in to be in the 100 years of quantum. And that's the other option that we're going to do is we'll have the papers being both in the special collection for the Bohm in Brazil, but also cross-linked to another collection that we have for papers pertaining to the 100-year of quantum mechanics. So it's sort of a double virtual issue, which you can do with the magic of the internet. So please, thank you. I've had a great time meeting everybody here and catching up with people who I haven't seen and have seen for the last 20 some odd years. So here you go.
Okay, so moving on to the next speaker. So next speaker is, I hope the pronunciation is right, is Maik Reddiger. So please, Maik.
Thank you very much. First of all, I would like to thank the organizers, Bill, Valdir, and Brett, for putting together this amazing meeting. So today I would like to talk about a solution to the time of arrival problem. I put in the term heuristic because the solution meets the standards of theoretical physics, but because I'm a mathematical physicist, I'm concerned about things being mathematically rigorous, and more work would be needed to make it fully mathematically rigorous, but I think by your standards you would be fine. I'm going to say what that means. So, what is the time of arrival problem? Just very loosely, before I give a more precise problem statement, you have a particle gun and some idealized detector surface, and you shoot the particles with the gun on the detector surface. And then the question is, how long after you trigger the gun do you notice an impact? And of course, quantum phenomena are probabilistic by nature, so you're not going to get well-defined time, you're going to get a certain probability distribution of impact times. And now the question is, how do you get this? Just from the quantum laws. Well, why is the problem interesting? It is interesting because it's actually been a long-standing, unresolved problem in the foundations of quantum physics So there's various proposals in the literature on how to address this. It's also been of interest to the David Bohm community because, well, just to highlight my point, Zidan Das, who was Detlef Dürr's last PhD student, just this year handed in a dissertation on this problem. And maybe to the wider physics community, it is interesting because our quantum mechanical concepts seem to fail us here. And in this sense, I would argue at least that it is an anomaly in the sense of Thomas Kuhn. So what am I going to speak about? Sorry. So I'm going to begin with a problem description. Then, first of all, I'm just going to give a problem statement and then also explain actually very insightful previous solution that I think is nonetheless wrong. So it's kind of pedagogical. Then I set up the ideal detector model via mathematical probability theory. This then raises the question of how to do the dynamics. And this dynamics is then taken care of, and then all we need is the formula for the impact time probability. And in the end, of course, I summarize. Just a little remark. So this is going to be a very mathematical talk. If some notation is unclear to you, and I haven't explained it, please just quickly raise your hand. But for more conceptual questions, please let's put this to the end. I'm sure there may be some. All right. So let's start with the description of the problem. So we consider a subset in a real three-dimensional space, connected, closed, possibly unbounded. You can, for instance, think of a closed ball or maybe the half space. So then, of course, we need a detector surface, and that's given by the boundary of the set. And it should be smooth in some sense. On that detector surface, we can then look at the outward pointing normal vector field. The direction is important for some of the signs and the formulas I'm going to show. We assume that the interior is non-empty, okay. So that's our space. And because we want to do dynamics, quantum dynamics, we start with some initial position probability density. And so what does this mean? I want to be open from the start. I have an ensemble view, what Jean Bricmont called the naive statistical interpretation. I very much subscribe to that. I have no objections to what he said, but I don't want to go into that now. But basically, you look at where you initially have your particles, and in a sense, this gives you the distribution. And what's going to happen? We also want no external forces. It's just for simplicity. We can adapt it if we want, but just start simple first. And we want to know how long does it take, or we want the impact time probability on the detector surface. And just qualitatively, what's going to happen? Well, quantum dynamics is going to spread this initial probability density. Part of it goes off to infinity, and the other part gets swallowed by the detector. So actually rather simple, you might think. And this brings us to the first main question. How do we actually model an ideal detector? And when you think about it a bit, you notice that this is actually a dynamical problem. So the presence of the detector has an impact on the dynamics. Why is that? Because basically those particles that hit the detector surface, we kind of want to take out of our ensemble. And so this matters because you could have so-called quantum re-entry, and some people don't do that. And what does this mean? This means that any solutions to the time of arrival problems or proposed solutions that do not take account of the fact that this is a dynamical problem cannot be fundamental. So let's try a natural ansatz, at least from the point of view of quantum mechanics. We want pre-Schrödinger evolution, and then how do we take account of this detector surface? We put a boundary condition at D. Rather straightforward. Of course, our probability density is given by the usual Born rule for position. And Werner actually proposed a boundary condition for this case in 1987, which is still in use today. And it is the following one. So the D just means restriction to the detector surface. And of course, N is our outward pointing normal vector field. And kappa is some complex valued function on the detector surface with these properties. And this is actually a very natural boundary condition, I would argue. So first of all, from the point of view of quantum mechanics, the answer is natural because you just take the usual Schrödinger equation. The equation as well as the boundary condition is formulated in terms of wave functions, and everything is linear. So for quantum mechanics, yeah, this looks really good. And I'm going to argue here that this is the wrong way to tackle the problem. So let's do some analysis. Of course, the Schrödinger equation gives us the continuity equation. We've seen that several times in this conference. Then you can reformulate the boundary condition. So you take the imaginary part of this effectively and get the following condition on the normal component of the probability current density vector field, which is essentially just given by the imaginary part of kappa times rho. Okay, and then you can ask, all right, what's the rate of change of the probability contained in omega? Okay, you just exchange differentiation, insert your continuity equation, then use the divergence theorem, and last you insert the boundary condition. And this is actually good because the imaginary part kappa is negative, and you have a minus here and the rest is positive. This is negative. So this means that the particle probability in your space gets reduced over time. So this is actually good, right? That's not an objection. That's actually a strong point about this. So this boundary condition does indeed ensure that the detector is absorbed. So what are my objections? Well, the first one is you have this really ad hoc function kappa thrown in, and it's not really clear what this means. And it's just coming out of nowhere. And when you ask what it means, you get to the second two objections, like the second and the third. And you find, okay, if you define your Bohmian velocity vector field, excuse me. No, this is if you define your Bohmian velocity vector field or probability current vector field, then you find that the imaginary part of kappa fixates the normal component of this. And this is somewhat strange because we really care about the probability current density going into the detector surface. And what you're fixating here is the velocity in a sense. So this is kind of weird at least. And if you do this the same with this stochastic velocity, which was called the osmotic velocity here, also, so this appeared in, I think, 3 talks already here, you get a similar condition. So these are 3 really strange things, and my argument is that this boundary condition is arguably unphysical. So what do we do instead? And the instead is we are going to construct an ideal detector model using mathematical probability theory. So just as a quick recap, mathematical probability theory was discovered or developed by Kolmogorov in 1933, a Russian mathematician, probably one of the greatest mathematicians of the 20th century. And he published his work Grundbegriffe der Wahrscheinlichkeitsrechnung, or in English, Foundations of the Theory of Probability, in 1933. So how does mathematical probability theory work? Well, the central object is a probability space, and that's essentially a measure space with a measure where the measure of the whole space is equal to 1. So lambda is your set. A is, in a sense, a collection of subsets. That's where you can say, okay, that this is I can measure probability for that. It's called sigma algebra, and P is the probability measure. And then the next important thing I would argue in mathematical probability theory is the concept of a random variable. So that's just a measurable function, here real valued, and measurable means you put some sigma algebra on R, and then the pre-image of such nice sets are again measurable with P. And mathematical probability theory then gives you a formula for the probability that your random variable takes values in, say, an interval I. And this is just, you just take the pre-image of that interval and the measure thereof. And it's given by this integral. And there's another way to write this, namely as the composition of x to the minus 1 with p, so x doesn't need to be invertible, actually. And we call this object here the probability distribution with respect to x. And lastly, the expectation value of x is just given by this formula, provided x is integral. So how do we apply this to our time of arrival problem? Well, we need a probability space, and for that, the central idea is to say, well, I'm going to introduce a surface probability density sigma on my detector surface, and then just make sure that this normalization condition for probability holds for all time. So if you want to formalize this, you have your probability measure, and it is given by the following formula. And then formally, you already have the probability space. So at least on this point, we're done, and it doesn't actually deviate very much from previous proposals at this point. And so let's have a look at what happens when we assume continuity. Well, we can just derive this condition. Looks like that. Then you insert the continuity equation, and then this suggests that you want to have the following formula for the rate of change of the probability surface density. However, this doesn't give you an absorbing detector. It is certainly valid, at least. I mean, there's nothing that speaks against it in principle, but for our purposes, it's not useful, because then we would need some other boundary condition on n times j, and we would be back to square one. So I'm saying, no, this is not going to work. So what do we do instead? Well, two ideas. The first one is we modify the continuity equation and introduce this sinc term on the right-hand side. So delta d is a Dirac delta on d, and r is a function on the detector surface. I call it the sinc term. And you can give a formal definition for delta d, but just for completion. And then you just do the same spiel. You derive your normalization condition, continue as before, and then you get this additional r here. And then this suggests that the following formula holds for r. Okay, that alone is not that useful yet, so we need a bit more. And the second idea is to say, well, I impose absorption. So we have a Heaviside step function, and we just force this rate to be positive. Well, it looks a bit artificial, but now if you combine it with the previous formula, you get this for the sinc term, and you can actually show the following. There is no probability flowing from d into omega. How do you show this? Here's an informal proof. So you consider your set. You want to take the probability off. You decompose the boundary. Basically, you look at the part that intersects the detector surface and the part that doesn't. And then this gives you a decomposition of this rate of change. And the first part we don't really care, because it tells us something about interchanging probability with the surrounding space. But the second part we very much care about, because it tells us how probability is interchanged with the detector surface. And we find this is negative. So you can only lose probability at the detector surface. So that means it's absorbing, and this works. So just to summarize, we define our probability measure as follows, using our probability surface density on the detector surface. Then our normalization condition is assured by asking that the initial data satisfies this, and asking for the modified continuity equation to hold. And the time evolution of the surface probability density, you can just integrate the rate and get the following formula. So again, what's the advantage of this approach? Well, you don't need a boundary condition. There's no boundary condition, and all you really ask for is the probability to be absorbed at the boundary. So it's very natural, no ad hoc function. Okay, but how do we square that with dynamics? Because we just modified the continuity equation, and we know the Schrödinger equation implies the continuity equation. So something is off here, or at least it seems so. And for that, I would like to remind you of the Madelung equations. Mordecai talked about this in their integrated form, here again for one body. So you have the following local equivalence. And what is interesting is that this single equation splits into two evolution equation plus a constraint. And the first evolution equation is in a sense giving you the dynamics. By the way, I'm using a formulation of the quantum force here due to Nelson. And the second one is the continuity equation. And so this means we can just keep the dynamical equation and modify the continuity equation. And we got our dynamics. So this gives us the following system of evolution equations. And this looks quite complicated. Well, to some degree it is. And this is not just a system of PDEs, but this is a constraint system of PDEs. But the constraints are actually not that much of a problem. They actually help you. Why? Well, first of all, you can require it for the initial data, and then you can just need to check that it holds for future times. And indeed, we already showed that if our initial data satisfies that, then the continuity equation always assures it, the modified continuity equation. And this constraint here is also assured. You just take the curl of the first equation. So that means all you really need to do is solve these coupled first two equations along with the constraint, and then in the end you can just integrate the third equation. It's not as evil as it looks. So that's our dynamics, and we call this the one-body Madelung equations in the presence of an ideal detector. So what about quantum mechanics? Well, formally you can actually derive a Schrödinger equation. I just did it in some previous work where I added such a source term and just formally plugged it in. However, the problem is this is nonlinear, this is not symmetric. It's quite strange, actually. So in the quantum mechanical context, this is kind of a nonsensical evolution equation. But we showed it was physically justified. So in principle, it's a sensible system of PDEs you can look at. So why not? Okay, mathematically, you still need to show well-postness, which is a bit more complicated than for the Schrödinger equation. So just as a reminder, well-postness means that you get a unique solution. You get a solution, you get a unique solution, and it's suitably well-behaved under perturbations. So this formally still needs to be shown for this to be a fully mathematically acceptable approach. But you can actually make sense of this model, not within quantum mechanics, but within a framework I've been working on, which is called geometric quantum theory. So just as a reminder, how does this work? Well, geometric quantum theory, first and foremost, is a research program, and it is, you can basically describe it via the following two core hypotheses. The first one is the fundamental equations of quantum theory are adaptations of the Madelung equations. And the second one is that quantum phenomena are described by mathematical probability theory. So these are hypotheses, and then you look at what does it predict. And in practice, the main difference is really that you throw out the quantum mechanical observables and replace them by suitably motivated physical random variables. And this may seem like it's never going to work, but actually, I was able to show that this reproduces center predictions of quantum mechanics. that you can make novel predictions. This is in the latest preprint, that for certain classes of models, you can have a mathematically rigorous formulation of this, because mathematical probability theory is well developed. There is mathematical formulation. And originally, it was created as a solution to the problem of first quantization under holonomic constraints. I just refer you to that paper if you're interested. It has a physically natural classical limit. I actually discussed this with Angel. Also, in a sense, it's where the Bohm force vanishes. Of course, it's a bit more complicated than that, but roughly speaking, that's how it works. And you can generalize this to the relativistic theory. So how does this work in this particular context? Well, generally, a model in geometric quantum theory consists of the following. It's really just a stochastic theory. Like any stochastic theory, you require a time-dependent probability space. That's just the Born rule for position, a prediction of time-dependent physical random variables, and a time evolution law. So the first one we already had. The second one I haven't talked about much. I'm going to do that in a sec. And the last one, the time evolution law, well, we just had the one-body Madelung equations in the presence of an ideal detector. So the basic random variables are going to be your position, your probability current velocity, your stochastic velocity, your probability current momentum, and your probability current angular momentum. And the energy random variable you can just get from the Madelung equation is given as follows. And then, okay, why would you use this? Or can you show that it's somehow more powerful than quantum mechanics? And indeed you can. So first of all, you can define the conditional probability of U given D. So basically, what is the probability of finding the particle somewhere under the assumption that it is on the detector surface? Well, that by itself is not too interesting, but you can then compute conditional expectation values. And here I just computed the conditional expectation value of momentum given D. And in a sense, this is a measure of how, on average, how hard the bodies hit the detector surface. And I don't think you can do this with quantum mechanics. Right, then let's talk about impact time probability, because that's what we originally wanted. So we need an impact time distribution. So provided that the detector is absorbing, you actually, oh, I'm sorry. You can actually say the following: the probability that you get an impact up until time t is the same as the probability that the particle is on the detector surface at time t. Now, why is that? Because the detector, because once the particle hits the detector surface, it just gets absorbed there. So that is why you can use this formula. This only works for absorbing detectors, but it works. And then because you say, okay, I want this to be a probability density or probability distribution, it satisfies all the usual rules for probability measures. And then you can directly derive the following formula for having the particle on the detector surface in a time interval t plus delta t. And this formula is actually not new, but I'm just saying this is how it works. And of course, then if you plug everything in, this is how it looks like. And this is very analogous to what was given by Daumer et al. In 1997, just with different dynamics and a slightly modified rate for the probability surface density. All right, so because I'm kind of a mathematical physicist, I also care about what is the underlying probability space. And this is interesting because you can look at the following limit. You can show it exists. And what does this limit give you? Well, it tells you the probability that the particle hits at all. And this, the interesting point is this limit need not be 1. It's also known, actually. So the probability that the body never reaches D is then 1 minus p infinity, just by the words of probability. And you get the following form of formulas, okay? And the following sigma algebra. So this is the smallest sigma algebra that you get by taking the usual sets and the event that your body doesn't hit. And then you can derive the following formula for the probability measure, check that it satisfies all the nice properties. And I would say that this is the general solution of the one-body time of arrival problem for ideal detectors. So just to summarize the results. So if you want a fundamental solution to the time of arrival problem, you need an ideal detector model. And the fact that you have an ideal detector, this modifies your dynamics. We propose dynamical equations, and this is given by, in this case, the free one-body Madelung equations in the presence of an ideal detector. And if you have a full solution, if you want to have a full solution in a mathematical sense, you need to show well-posedness. So that's for the mathematicians here. This ideal detector model is incompatible with quantum mechanics, as was shown, but you can actually make sense of it within the framework of geometric quantum theory. And this is a novel adaptation of quantum mechanics based on mathematical probability theory. And the formula for the predicted impact time probability in principle has been proposed already by Baum et al. In slightly modified form. But in principle, I do not really deviate from the literature here. And as an outlook, what more can you do? You can look at many body generalizations. I was actually able to derive something for two bodies already. And if you have two, you have n bodies. You can then include spin and electromagnetic interactions. You can look at relativistic models. And of course, in the end, you need to test this experimentally because physics is an experimental science. So this is, in a sense, I would say, one of the most important things to check this. And just as a final outlook, which I think would be fun, so you can actually do this with the double slit experiment. So you have your initial electron probability density, you model the two slits by imposing a homogeneous Dirichlet boundary condition there, and then you insert your ideal detector model on the screen, and then look at the dynamics. What does the dynamics give you? And the nice thing here is that this probability surface density actually shows you how the interference pattern builds up. And of course, the final interference pattern we expect to be given by this limit. And I would finish with a note by Landé, which is here paraphrased. So he said that in electron quantum experiments or material quantum experiments in general, we always measure particles, and it's only the statistical behavior that is wave-like. And in particular, the fact that we have this wave-like statistics does not violate the idea that quantum theory actually describes particles. So with that, I leave you, and thank you for your attention.
Thank you for the talk, Mike. And we are open for questions. So any question?
Thank you for the nice talk, Mike. I just have some comments. Can we go to slide number 17 or 16? I don't remember well now.
Sure. Oh, I cannot press this. Give me a sec. How do I? Yeah. 17 you say?
17 or 16? This is
Okay.
the one when you introduce this nice nonlinear Schrödinger equation.
Right. Okay.
Okay, here.
This one.
Yes. Yeah,
Yeah.
this one. You said that it is overly incompatible with quantum mechanics because of the nonlinearity, but
Yes.
I have a comment against this statement because, I mean, actually, when you describe realistic situations or realistic or more realistic situations, nonlinearities and time dependencies and all this weird stuff that is hard to treat from a mathematical point of view already appear. Just two examples. For example, if you consider the case of a sound laser acting on an atom as laser pulses, you have a sound dependence on time. This is what gives you the high harmonic generation phenomenon. if you consider also very strong electric field, you are going to have the Kerr effect, and therefore there you are going to have terms that depend on psi square and many other things. So, and these equations are perfectly valid and actually necessary, because with this you cannot, with the what you call the linear Schrödinger equation, you cannot go beyond that. Also, when you have to treat molecules and you have many electrons over there, you come up with the Hartree-Fock approximation, where you have all these interactions. I mean, this mean field. No? Yesterday in David talk, we saw that the interaction between two surfaces for dissociation and all this stuff. There we have also non-linearity. So what I want to say with this is that maybe it is not so nice to work with this because it's difficult, but still they give you a more, situation closer to the reality that you want to describe. On the other hand, well, Schrodinger's equation, this is as such, the linear version is just an approximation in the non-relativistic case.
Well, I look at this from a foundational perspective, so from the perspective of the Dirac-von Neumann axioms, and the fundamental axioms of quantum mechanics require you to have this linearity. In actual empirical models, people don't really care much about that. I totally get you, but I'm really interested in foundations, and for me, the question of how far can you go with mathematical probability theory, and in particular, when do you actually break the quantum axioms is really what interests me. And I was also drawn to the problem because here you obviously break some of those fundamental axioms, and I would still argue that this is a valid empirical model. Of course, we need to test it, yes.
Yeah, but the foundations, there's a problem, and we have seen this along this week. The foundations without the assistance of the experiment, of the reality, go nowhere.
Yeah.
So, and actually this is what David Bohm liked to stress, and also Basil Halley. We have to be close to the experiment to see whether what we are doing is correct or not. This leads me to another question with respect to the kappa that you mentioned at the very beginning. That you said something, or I remember, correct me if I am wrong, that it is unphysical, or that you don't understand where it comes from.
Right. So first of all, that it is ad hoc. It basically comes out of nowhere. You agree with, right?
No. But that's the mistake. This kappa actually comes from the absorption.
Okay.
So
how about
physical
this?
effect?
So actually, I talked to Zita and Das about the topic, and I don't know if he's right or not. I was just quoting here. So he told me that this boundary condition actually gives you the wrong time of arrival distribution. So empirically, it is not correct. And I'm kind of more of a theorist, and I look at what could be wrong with it, or is there anything wrong with it? And I would say, yes, it is quite unnatural to say I fix the normal component of the probability current velocity vector field on the detector surface, because it's strange, right? You basically say your probability has to flow into the detector with a fixed velocity at least fixed normal component of the velocity at every point. That is, I just find that objectionable. Okay.
You use term wrong probability, time of arrival probability, and you use term ideal detector. But as a physicist, I know there is no correct or incorrect. It's all depends on all kind of detector. And the ideal detector, which will tell you exactly the time of arrival, what I believe, will not detect anything. It's a Zeno effect will prevent any detection. So you have to specify what is exactly the physics of detector, and then for every detector there will be different time of arrival probability.
So in principle, I don't really disagree with you, because obviously there is no such thing as an ideal detector in nature, right? But for this detector model, you assume that it's non-interacting and that all it really does is swallow the particle. That's really what.
This is really not physical.
I think so. Hear me out. I think one can have certain cases where this is a good model, just like we do things in physics as usual. Yes, and what are those cases? Well, there's not that much interaction of the detector with the particles, and basically the detector measures the particle and then it's out of your ensemble. That's basically the core assumptions. Thanks.
Okay. Not enough I'm defending you or not, so but I'm not sure. But if okay, if you take a detector, once the particle collides with the detector in a very real way, and we register its, let's say, position. Once that is registered, then where the particle goes over after that is actually a bit irrelevant from my perspective. It obviously still exists.
Yes.
It doesn't cease to exist. But the point I'm trying to get at is that we have converted that into an electronic signal, which gives us the register that it's there.
Yes.
And we can register to a certain, within obviously errors, what time it does arrive. So we can do that.
Yes.
Now, whether we could do that to the degree of accuracy, like statistical error, that would be required, is of course a matter of design and debate, obviously.
Yes.
But in fact, so when we talk about absorption, it's not absorption. I'm not quite sure what you mean by absorption, but the point is that it does. I mean, in my case, the electron, actually does enter. It bounces along and enters the detector, and so therefore, but once we've got the electronic signal from that, whichever mechanism you use, what happens to the particle afterwards is actually irrelevant. I mean, it's played its role.
Yes.
And so I think, and as I say, the word absorption is probably, I'm not sure it is absorbed. I'll tell you what has been absorbed is the energy from the particle.
Okay.
Because we've taken that energy and converted it into an electronic signal.
Okay.
So maybe that might be a better way of looking at it. I don't know. But anyway,
No, so actually I was thinking about that as well. So I gave you this formula for the conditional expectation value of the momentum, but you can do the same with energy. Of course, there's a little bit of question of interpretation, what is what, but in principle you can compute it. Second point is, that's really the core assumption of this model, that after the particle hits the detector, you throw it out of your so-called ensemble. You don't care about it anymore. And that's why there can be no such thing as what people call quantum re-entry, or incorrectly quantum backflow, because you take out that particle. It cannot go back. That's one of the core assumptions, core empirical assumptions, and this ideal detector model is based on that. Okay. Thank you.
One more question? Okay.
This is just kind of a follow on what Bob was asking. So you've characterized the absorbing detector by just having the probability current disappear. You have a sync term that makes it vanish. And that raises the question, where does it go? Where is the electron in your model? And one of the ways you might deal with your nonlinear term is to actually kind of treat the electron on the other side of that process and get another term that sort of is that is absorbing it. Sorry, the term has a source function instead of a sink function, such that those two are in parity.
No, I mean, as I said, so I take an ensemble view. That means for me, a the wave function, so to speak, really represents a statistical ensemble, and an ensemble is made up of many samples. So that's, in a sense, all the experimental trials you could ever make. So an ensemble is an abstraction, just like a wave function is an abstraction. And what I'm doing here in this model is to say, well, I don't really care where the electron goes after it hits, but it's convenient to model it in such a way that it sticks on the detector surface. And there's no more interaction, so we can perfectly do that. That's one of the core assumptions, I would say, of mathematical statistics, is that the samples do not interact with each other, right? So yeah, that's the idea.
Okay, we have to move on for the next talk. So thank you very much, Mike. And the next talk is, again, another remote talk, and Chris Dewdney is going to talk about what we have learned from the quantum trajectories. So please, wherever you are ready.
Okay, so I'd like to thank the organizers, of course, for the meeting, and indeed all the participants who've taken place in the meetings. It's been a fascinating and stimulating conference. A little bit frustrating to follow it all online and, of course, miss out on the all-important informal discussions. But for the end of the conference, I realized some time ago I gave myself an impossible title. In the last 25 years, or possibly longer, there's been an explosion of interest in de Bohm. And so, to try and summarize what we have learned from all of this work is, as I said, an impossible task. Conference, I realized some time ago, I gave myself an impossible title. In the last 25 years, or possibly longer, there's been an explosion of interest in de Bohm. And so, to try and summarize what we have learned from all of this work is, as I said, an impossible task. So instead of trying to do that, I'm going to concentrate on a retrospective, really, of work I carried out last century, in fact, and what we learned from that about foundational issues in quantum mechanics and the de Bohm theory in particular. Now, I've always thought that de Bohm theory is just quantum theory. But in my education and intellectual development, there have been really a series of shocks. So you grow up in the classical world, everything's very straightforward. Physics doesn't really have any major issues about what it's about. And then, of course, you get taught quantum mechanics at university, and you start wondering what that's about. And you start reading Bohr, and you realize that somehow the world has disappeared. There is no quantum world, and that God does play dice, and that probability is inherent. But so that was a shock, really, in one's educational development. But after that, there was another shock caused by these two people who, of course, Louis de Broglie and David Bohm, who showed that actually what Bohr said, although consistent, there's nothing that you can say is absolutely wrong with Bohr, apart from his philosophical approach. And when you read more into Bohr and you read things like atomic physics and human knowledge, you realize that all of his stuff, all his arguments didn't really come from quantum mechanics. They were sort of imposed on quantum mechanics from his basic philosophical approach. Anyway, it was a revelation to discover Bohm's interpretation when I went to work at Birkbeck just by chance, and I'm sure we've discussed that in other places. Also, I'm sure that I don't need to rehearse the form in which Bohm published his 1952 theory, which is showing on the screen now. It's very well known, I think. And I've sort of distinguished the two versions of Bohm's theory. I don't think Bohm would have liked the term Bohmian mechanics, although it does elevate him to the status of Newton, of course. because, you know, any sort of deeper reading of Bohm would tell you that he did not see his worldview as mechanical, but that's another whole philosophical discussion there. So there are these two versions, the second order version in which we have a force produced by the quantum potential and a particle velocity given by the gradient of the phase of the wave function. There's also this other approach which says, well, forget all that baggage, that extra stuff. Let's just take the guidance equation and describe that as the only equation you need. In actual fact, it is the only equation you need when you calculate trajectories. And let's say that the wave function itself is nomological. We've heard some stuff about that during this conference. So I went from being a Bohrian, I wrote my dissertation at Cambridge on Niels Bohr, and I was a Bohrian. I wanted to carry on working in this kind of area, but with more physics in it than I was getting in history and philosophy of science at Cambridge. And I asked my tutors about that, and they said, well, if there's only one place you can really go where you can do that, and that's go to Birkbeck College, which is what I did. And then we produced in story, which has been rehearsed many times, the trajectories and quantum potential for the two-slit experiment, and also the trajectories and quantum potentials for that other favorite of undergraduate quantum mechanics books, quantum tunneling. And it was just amazing to me at the time to see just how straightforward Bohm's approach was and how it gave, you know, a beautiful, clear picture of what was happening in the quantum world. And the other thing I really found attractive about the Bohm theory was that actually you could do something with it. You know, there was something to do. It wasn't just something to say. You could go away and calculate trajectories and really find out how it worked in detail. And of course, that's what I spent, well, probably quite a lot of my life since then doing for different circumstances. One of the ones we looked at after looking at those two examples was Wheeler's delayed choice experiment in the form of, you know, this basically a two-slit experiment with cross beams. You have some mirrors here, which send a beam from this slit to that detector and the beam from this slit to that detector. And so you might think that, you know, if that detector fires, that's because it's come from that slit. But as we've already seen, this is not the case when both slits are open. That simple sort of classical intuition turns out to be wrong. In fact, it's really not, it should be prohibited really, because we're talking about quantum mechanics, not classical mechanics. And where Wheeler's delayed choice comes in, of course, is that he argued that where you could either put in a photographic plate in the interference region and record the interference, in which case you would say the particle in some sense had to come from both slits, or you take this out and just record which detector fires, in which case, argued Wheeler, you could say from which slit the particle has come. Now, two things about this. The first one is that, of course, in Bohm's theory, it can't be true that any decision you make now can affect what has already happened. And in fact, you can see just from these pictures here that the interference pattern is there when both slits are open, regardless of whether you put your detecting screen in there or not. And so in a sense, this is already real. Okay, to refer later to the surrealistic trajectories, this is already surreal because the detector that you expect is recording a particle coming from the slit it's pointing at, in fact, is recording the particle which came from the other slit. And in fact, this behavior, of course, was exploited in the surrealistic trajectories later on when you put a detector in one of these beams. And as Lev explained very clearly in his talk, it depends whether that detector is fast or slow as to what the outcomes are, how it works. And you get this situation where the detector can be seen to have fired even when the particle's on the other path. And I noticed in Lev's talk, he said, well, you know, he didn't believe that at first. Well, I'm sure he remembers that I didn't believe it either at first. And there was at a conference where Lev and I had long discussions, and eventually any objection I could come up with was squashed. And I had to admit that actually this was a real effect. Anyway, so what did we learn from all this early work? Well, it's the big lesson, I think, and that big shock really, is that it is possible to conceive of a definite and deterministic quantum world, and to quote Bohr, a mode of description which fulfills to a higher degree our accustomed demands regarding the pictorial relationship between cause and effect. So here is a quantum theory which has absolute objective ontology as opposed to the probabilistic and observer-dependent nature of standard or Bohrian quantum mechanics. And for me, at that time, seeing all of this stuff come out of the computer was an amazing thing, particularly having been a Bohrian. And the quantum world somehow emerged in stark relief from this vague fog of Copenhagen. Now, all of this, of course, has been known since 27 and 1952, but it was generally ignored. All this history as well, rehearsed as well. Oh, I just realized I didn't start my timer, so someone else is going to have to help me on that. I'll start it now. Yeah, so I think these pictures that we produced in the 70s and 80s, you know, had some impact in the physics community, and certainly from the 90s onward, as various people have shown in citations, the whole theory took off. So what we discussed so far was very fundamental quantum processes and how they could be explained in Bohm's theory. So the next thing I decided we needed to look at, of course, was quantum measurement, one of the most discussed features of quantum mechanics. And in order to do this, I thought, well, let's look at spin measurement. And this is where Brazil comes in, because when Bohm was in Brazil, he worked with Schiller and Giomno, and he produced a theory. He extended his theory, really, to include spin. And in these, I won't go through the theory, I'll just show you the pictures. But the spin vector, which you can define, is just given by this expression, and the Orr velocity is given by this expression, where psi, of course, is a two-component Pauli spinner. So it was fairly straightforward to extend the calculations I'd done to this case. And so what we see here in this simulation I'm about to show you is a magnetic field represented by the vertical lines. It's stronger over here than it is over here, so it's a field gradient. This is the probability density here, and this is a narrow packet at the beginning of the experiment, which then splits into two. Hang on, let me pause that a moment, if I can. Oops. Yeah, so the initial state of spin state of this particle is that it's in an eigenstate of sigma x in the positive x direction, and the field is in the z direction. So we're measuring spin in z, and the initial state is an eigenstate in x. So let's see what happens. At first, the particle just processes, the spin processes around the magnetic field, but as the packets begin to separate in space, the spin vector is twisted and begins to point downwards if it goes into the lower of these two branches in the wave function. And it begins to do the opposite thing. So it starts processing, and then as it goes along, that direction of the spin vector then turns to be pointing upwards. And so we see that what's happening here is that a so-called measurement isn't actually a measurement at all. Okay, it's unless you're measuring an eigenstate, in which case it would give you that answer. But so what we're seeing here is the way in Bohm theory the actual values of, in this case, spin, are changed through the interaction so that initially they're not an eigenvalue of the operator you're measuring, but at the end, they become an eigenvalue. Now, this actually comes in every example you care to think of a Bohm measurement. If it doesn't start in an eigenstate, the evolution of the system will produce you a particle which has the appropriate properties for the eigenstate that the particle actually enters in this packet. So that's a very, I think, very, this is a relatively recent version of the calculations. It's just prettier than the ones we published back in 86. And so what's our second lesson then? This is supposed to be about lessons we've learned. Well, measurements in quantum mechanics are not faithful, except for position measurements and eigenstates. And quantum measurements aren't really classical measurements, measurements in the sense of classical physics at all. And we've seen from that simulation, it happens in all cases, how de Broglie-Bohm actual values evolved to become measured eigenvalues through the dynamics of the measurement process. There's no wave packet collapse required to get a definite outcome because there's a definite particle trajectory, and unique outcomes follow from unique initial conditions, and there's no need for observers or their friends or their cats or anything else. The second shock, having seen all these calculations of how things work, one gets a bit seduced into thinking, well, this is a theory in 3 space and time. It's in ordinary space, you know. We're just seeing the effects of superposition. It's apparently a wave which propagates in the 2-slit case through both slits and affects the particle in between. But I think this is, and this is really, I don't know what number of shock I'm on now, but it's another shock to find out that actually that's not the true nature of quantum mechanics. And that although superpositions are fundamental in quantum mechanics, it's really superpositions in configuration space, which contain, if you like, the essence of quantum mechanics. Of course, in the single particle case, when you've got apparent 3 space, it really is configuration space, but it's just the same as ordinary space. So the first example to look at, and this was from the Infinite Potential film, I made these animations with Kalin Diak from Romania. And yeah, so I won't go into the details of how we did it, but these are the actual trajectories, not just drawn in. And I want to consider what happens when we put a detector into the situation. So there's a detector sitting just here between the slits, and it's firing depending on which slit the particle goes through. And this box over here is really showing what really happens in the full description, which is in configuration space. You'll see here these trajectories are crossing in the real space. Why do they cross in the real space now, given that they were interfering in producing the wiggly trajectories which went into interference patterns? Well, it's because the quantum description now has to take into account the fact that you have a detector with a quantum state, there's a coordinate for the detector, and that coordinate changes as the process takes place. So let's have a look at a little more detail on this. So the detector has a state labeled by D, it has a coordinate labeled R, and the interfering particle has a coordinate X. There's the left slit and there's the right slit. If the particle actually goes through the left slit, if the detector sees the particle going through the left slit, its state changes from this blue one to this red one. They're non-overlapping and it happens fast. So there's no surreal business going on here. Or if you replace it with a slow detector, there would be. If it goes through the right slit, the state moves down here, the coordinate moves down here. So if we represent that in the configuration space, you see what actually happens is that these two sets of trajectories from the slits, which were overlapping in the configuration space, are now separated out. And so they no longer overlap, and so there's no interference. But the description has to be in the configuration space. And down here at the bottom of the slide, you see how the wave function evolves. Right, so the next lesson I think we learned from this is that configuration space is the fundamental arena for quantum mechanics. And when you introduce measuring devices, you're inevitably increasing the number of dimensions of the combined system's configuration space. And the apparatus and the measured system are now described by a single inseparable entangled configuration space wave function. And from this, of course, it's in configuration space, but we can define a conditional wave function for an individual particle. We do that just by specifying all of the particle coordinates except for one, which will then give you a function of just one coordinate. This was actually first proposed back in 1990 in a paper I did with my PhD student, Monet Lam, on locality and non-locality in correlated two-particle interferometry. So the well-functioning measuring device separates the, as we've just seen, separates the configuration space wave function into non-overlapping channels. And this prevents interference in this case. And you can say that, well, if the detectors also have decoherence, and there's a wonderful description of decoherence in Bohm's 1951 quantum theory book, we can also say there's an effective wave function, which is the wave function associated with a particular channel that the particle has entered. So I think what I would like to argue is that many particle quantum mechanics really contains the essence of quantum mechanics, and its superpositions in configuration space, which are actually, in a way, the fundamental feature of quantum mechanics. Of course, that becomes superpositions in three-dimensional configuration space when we only have one particle. And so I thought, well, what is the archetypical experiment that one could look at, apart from EPR, which we'll look at in a minute? And I thought, well, it's really the Hong-U-Mandel experiment. And this experiment basically is very simple. You have two lasers pointing at a beam splitter. There's one particle coming from the laser pointing downwards, and there's another particle coming from the laser which points upwards. And the effect is that if the particles are bosons, and of course the experiments were initially done with photons, then they both come out on the same side. And the question is, well, how can this happen? How does it know that when one particle has gone one way, that the other particle has to follow? It seems, if you think about it in real space, just a real puzzle how this could be. And in the fermion case, of course, the particles must always come out in different channels. And again, that's a puzzle. How does it know? How does one particle know to go to the other channel? So it's a clear case of non-locality. So I said about making a simple one-dimensional model of this experiment. It's something which is always worth doing, to make these one-dimensional models. And the reason for that is that if they're one-dimensional and you have two particles, your configuration space is only two-dimensional. And so you can picture it. Of course, once you go, if you have two particles in 3 dimensions, you've then got 6 dimensions of configuration space, and you can't really draw it anymore. And I'm rather attracted to the idea of drawing things that you can actually see and get an intuitive understanding of. So this is the model here. There's a wave packet psi A of representing the particle from one beam, another wave packet psi D representing the particle representing the beam coming from below. And of course, these waves get separated into a transmitted part and a reflected part at the beam splitter. But the model, all we really need to do is to have these two wave packets approaching each other and represent the beam splitter by a barrier which has a transmission of 1/2. Now, if we input a simple product state into this situation, so that in this case, let's say we know that particle 1 is in the wave packet A coming from on top, and particle 2 is in the wave packet coming from below, then that's a product state. We wouldn't expect any funny business with that. We'd expect each particle to behave totally independently of the other particle. And of course, that's what happens. And so in this case, the initial state is just one peak in the configuration space. And I'll show you this not because we have to use configuration space here. Of course, we don't have to, because everything is local and particles are obeying their own individual equations. But I'll just show, so we've got one peak, and as it evolves in the configuration space, there's lots of interference, and eventually we get the same amount of probability, roughly speaking, in each of the sectors, representing, you know, both going up, both going down, and the ones where they go to opposite sides. So I'm not going to pursue that anymore, because although we can represent the whole thing in configuration space, we don't have to. The situation is completely different now if we input an entangled state. So here we've got the case where we don't know whether particle 1 is in A and particle 2 is in D, or it could be that particle 1 is in D and particle 2 is in A. So we have this input entangled state there, which leads to an output entangled state. And now we cannot separate this equation into individual particle equations. So we have to solve the two-particle or two-dimensional Schrödinger equation. And incidentally, of course, there's no distinguishing a two-dimensional Schrödinger equation, which is describing two particles in one dimension, from a Schrödinger equation which describes one particle in two dimensions. So our initial situation here now is that we have our 1D model space as before, and the configuration space now has two wave packets in this entangled state. And if we do the simulation, we work out what happens. I hope you can understand the diagram. This configuration space, that's X2, this is X1, and these two blobs here represent the two wave packets, the two possible scenarios which are happening. And if we run the simulation, again, we see lots of interference as the particles hit the beam splitters, but now all of the probability is going into the plus state. They're both above, or they're all going below. Now, the question then is, can we work out the Bohm trajectories for this? And, you know, after working out loads of these trajectories, it's somewhat disappointing, I suppose, to find that actually you can always say what they're going to be without grinding through all those calculations, just by knowing that the trajectories in configuration space cannot cross. And in this particular case, if we look at this horizontal, this diagonal dotted line, and you work out the velocity along that line, you find that the velocity perpendicular to that line is actually 0. So they can't cross that line, right? They can't cross that line, but they have to go into these two outcome probability density packets in the plus plus and the minus minus. So the only way they can do this without crossing is if the ones above this red line in the initial packet there are going to go to the plus plus sector, and the ones below that solid red line in the initial packet are going to go to the other one. And of course, there's another packet on the other side which does exactly the same thing. So we don't have to work them out, but of course you can. And if you do, we see these trajectories for bosons. So this is the configuration space time on the upper left. If we project that down into X1, X2 space, we see the trajectories over on the top right, which are showing this feature that they don't cross that line. And if we project onto the X1T face, we project into the space of X1, then we get lines which cross. Okay, and if we simply change the sign in the wave function, then we get totally different behavior, as shown here. Now, I thought I'd make this simulation because for me, this simulation really brings to the fore very clearly the situation I think we find ourselves in here. So over here on the left, let me just explain, we have the configuration space, and we've got these trajectories shown in faint gray. The simulation is going to pick some initial starting point, either in that packet or in this packet, and follow it through. And then over here on the right-hand side, we have what's happening in real space. So let's just have a look at this and see what's going on there. And we see, if you concentrate on the image on the right there, we've got these two particles coming in, one from above, one from below, and somehow they know that they've always got to go the same way in this case. And then you think, well, how can this be? What possible thing would make this reasonable to see? And you obviously then have to have some kind of non-locality, some kind of interaction mediated perhaps by the quantum potential in real space, which is bringing this about. But I think at this point, we're already a bit stuck. And, it's a bit mind-boggling to think we need this kind of thing. But if we look over on the left-hand side at the configuration space, everything is perfectly clear. Everything is local, of course, in the configuration space. And we can see that the non-locality the apparent non-locality perhaps, that we see in real space over on the right-hand side is just a feature of the motion in the configuration space. Okay, it's very similar for the fermions. But I think I'll skip over that because in the interest of time. So what's our lesson 5? So configuration trajectories in configuration space are what is fundamental about quantum mechanics. Space-time trajectories can only be recovered by the projection of these configuration space trajectories into everyday space. Then in the 3 space, the trajectories appear non-locally correlated. Now, once we really sort of dive into configuration space, if you like, start thinking in configuration space, then we realize that something like the serialistic trajectories and all other 3-space puzzles become totally understandable and clear in configuration space where quantum mechanics actually evolves. And another example of this would be the EPR. I mean, Jean talked about this earlier. Well, back in 1988, we did the detailed Bohm calculations for this and then used them to produce the simulations for the infinite potential film. And so these trajectories, again, are not just drawn, they're actually calculated. And you can look at what's happening here. And if you look carefully at this plane here, this is showing where in the middle here, this is showing where the particles enter their respective slits. And the rule which appears immediately is that if the particle on the left is below the one on the right, then that one goes down and the other one goes up, or if it's the other way around, it's the other way. So you can see that from the simulations, and this is the rule which we deduce from this, okay? So it's just about the initial positions, which way they go in this experiment. And again, you might think, well, what on earth's going on in real space? This is very strange. But if you formulate it in configuration space, in the case of simultaneous measurement, this is very straightforward, because here we have the Z1 and Z2 axes, and what distinguishes where the particles go as this wave packet separates into the up-down and the down-up packets is simply where the particle starts, so or where the 2 particles start. If below this dashed line, then they're going to go into the up-down state, and if they're above that, they're going to go into the down-up state. And look, that's immediately obvious from just drawing it in configuration space. More than that, of course, if we turn off one of the detectors, then we find that rule no longer applies. And that even though the particle on the left here is starting from a higher point in its respective position in its slit, it becomes a down particle. So then, again, that looks odd. Just switching the detector on or off over here changes what happens to the particle over here. Well, that's just non-locality. So again, if we draw that in configuration space, again, it becomes intuitively obvious what's going on. So in the box there is when the second Stern-Gerlach is turned off. Okay, so the packet's initially centered around Z1 equals 0, Z2 equals 0, separate to the left and right of the Z1 axis, as that's the only magnet which is operating. And already when it's done that, of course, the state has become either 1 up, 1 0 or 0 1 up, down or down up. Because the coordinate Z1 has entered one of the packets, and that singles out this channel in the configuration space. So then if we then measure the particle 2 using a Stern-Gerlach, we know that all of the trajectories from the respective packets either have to go up or down. And again, it's blatantly obvious when you do it in configuration space. So what we see from the EPR calculations we did is that the motion of an entangled particle can depend, okay, non-locally when we describe it in real space, on the position of the second distant particle, but also that altering any of the parameters at the second distant particle location can non-locally affect the motion of the first. And if we draw it in configuration space, it's absolutely clear. So we made all this very clear back in 1988 when we first did these calculations, and they've often been rediscovered since. Problems, of course, when you have this, we have problems with relativity. You have to, it appears, because the outcomes, the Bohm trajectories are going to depend on the frame of reference in which the calculations are done, and this seems a bit odd. Of course, the immediate response is, well, this is a non-relativistic theory, so what do you expect? Bohm, of course, himself was well aware of this problem, and he said, well, all we need is an absolute frame of reference, which is not at all in contradiction with relativity. And in that frame of reference, the non-locality is instantaneous. Of course, it's a hidden frame. You can't discover it by any measurement. Of course, there's a bit of a tension there with relativity. And as we heard argued earlier in the week, both, I think, quantum mechanics and relativity are in conflict there. But perhaps it's, perhaps relativity needs to be changed or reinterpreted. And Bohm argued that while Lorentz invariance is something that was only applies at the statistical level to sets of measurement results and the statistics. And of course, the statistics are Lorentz invariant. So you'd have an underlying non-Lorentz invariant process, which is seen as Lorentz invariant at the measurements. So where does this lead us in terms of discoveries about quantum mechanics? Well, I think for me, you just learn that everyday three space and time are not the fundamental arena for quantum dynamics. And of course, if they're not the fundamental arena for quantum dynamics, then they're not really the fundamental arena for anything. And that, the relationships governing space-time motions of objects are not determined solely by their positions and interactions in everyday three space. You just can't get your head around that when you deal with these quantum phenomena. So what happens on Andromeda significantly can affect what's here on Earth. So what about the three space world in which we inhabit then? How are we going to reconstruct that? Well, we have to show that the three space world emerges in a natural way from this configuration space description. And there have been some recent papers, one with the title Living in Configuration Space, for instance, which sets about showing how this happens. But it's really a bit like the emergence of the classical limit. But I don't think this is resolved. There's very many different ways of thinking about this, and I think it's fair to say now that there are probably as many interpretations of de Broglie-Bohm theory as there are interpretations of quantum mechanics. So I think it's usually a sign of progress in a theory if there's some debate and different variations of it. So I've just put up here some of the possibilities adopted by various people when considering what it could possibly mean if our reality is fundamentally in configuration space. Even within the de Broglie-Bohm theory, I think there are different options. Of course, in classical mechanics, we can use configuration space. We don't have to, but we can. And of course, in a point in the three-dimensional configuration space of this chair, say, just means the chair is in a particular position. But somehow in quantum mechanics, that chair has to emerge from the quantum dynamics as perhaps the packet becomes concentrated around the same point as the classical case. So this is far from resolved, and it's far from comfortable. I'm trying to get more comfortable with the idea that what we see around us is just emergent from this deeper level at which reality exists, in which the wave function in configuration space constitutes, along with the Bohm miraculous point, as some people call it, constitutes the reality. Now, I'm sorry if you're disappointed by the title of my talk. We've learned a lot more from quantum trajectories than I have discussed here. Trajectories also have provided new ways of calculating, new theories, new ways of understanding cosmology and more. And I think we've seen that over the last years, and particularly we've seen it very clearly at this conference, just how fecund Bohm's theory is. All the different approaches and theories and ways of understanding that David Bohm and Louis de Broglie before him allowed. So, and I think it's, if we had just listened to Bohr the whole time, then I don't think any of this, of course, would have happened. We'd have all just shut up and calculated, been happy to just predict where our pointers and dials are on our measuring instruments and not think about anything else. But as Bohm said, one of the statements which he oft repeated and sort of sticks in the mind is that the thing is that physicists, they talk like Bohr, but they think like Einstein. And I think whenever you talk to somebody about this stuff, it's true. That is the case. You can see them. They retreat to their Bohrian Copenhagen safety because it is safe there. There's nothing wrong with that approach. But if you want a bit more, physicists generally want a bit more, then this is a possibility. I think perhaps I'm probably running out of time, but just one last statement is that I think that another great advantage of what Bohm and Louis de Broglie did was they showed us this alternative, and you can then use this alternative as a kind of touchstone, okay, philosopher's touchstone, if you like. So if anyone says, look, quantum theory has shown us that there are multiple universes, many worlds, it's been proven by quantum mechanics, you can just have a quick look at the Bohm theory and say, well, is it in Bohm's theory? Some people might say, yes, it is, because Bohm's theory is just many worlds in denial. But the point is that if something doesn't happen in Bohm's theory, then you can say, no, quantum mechanics doesn't teach us that. Okay, it doesn't teach us that the mind can affect matter. It doesn't teach us that, your consciousness and your friends collapse wave packets. because it doesn't happen in Bohm's theory. So you can say, well, that's just a point of view, right? You can't say that quantum mechanics has taught you that because it doesn't happen in Bohm's theory. So I noticed that the Brazilian flag has order and progress blazoned across it. So I thought we could suggest a variation on this for the Brazilian flag and call it the implicate order and progress. So implicate order certainly given us progress. Okay, so I'll stop there, and thank you very much for your attention, and thank you for this wonderful conference.
Well, thank you very much.
Maybe it's not so surprising. I agree with almost everything technical which you said, but your main message is that fundamental arena is configuration space. I cannot agree. Arena was about gladiators when they fight each other. So the arena, it's where the interaction happened. And the interaction happened in 3D. So we interact in 3D, and particles, their waves, interact and influence each other in 3D. And the locality is important in 3D. And what you put about many words, that it's emergent, emergent in branching or something like this. No, many words is fundamental in 3D. When you go to branching, then within the word you might see some non-locality. In many words, you don't need any special Lorentz frame. It's completely relativistic. It's local, no action at the distance.
Yeah. Okay. Well, yeah, I totally accept what you're saying, and I understand your views on many worlds. But I think I'd just say, well, we don't have many worlds in Bohm theory, so we can't say for sure that's what quantum theory has told us. And if we want to talk about gladiators and bullets in wave packets, then we've got to do the proper calculation and work out from the configuration space how that is described in 3 space, because it's true, you know, we have to specify the interactions in 3 space, but we have to then calculate in configuration space, and we've got to see the way the waves interact. Of course, you can't do it in 3 space apart from the previous talk where there seems to be a way of doing it. You have to use the configuration space. So there aren't really any waves in the real space. Or if you want to say that there are, you have to say, well, the way they interact is not according to individual wave equations. Okay, but I don't think we're disagreeing really. They're just 2 different points of view.
Okay, it's not the time, but I disagree about the point. I think the waves affect each other locally, but this is not maybe for now.
Any more question or comment?
I have a question.
Yeah, I think Jean has a question there on the Zoom.
It's more a comment than a question. I thought the talk was really extraordinary and very convincing. I don't see how anybody in the standard physics community, I'm not talking about, let's put it aside the many world business, but the standard physicists who are Copenhagen and so on should be convinced by all your pictures of what Bohm can do and resolve all the paradoxes, the delayed choice and delayed choice and all these things. That is really beautiful. On the other hand, I have a lot of sympathy for what Valdir was defending of the idea that the fundamental entropy is in space-time, and so you have phenomenology of particles that are guided by the wave function, which is defining configuration space, but nevertheless, I think it's important to think, I mean, I wouldn't say that the 3-dimensional space emerges from the configuration space. I would rather say that the 3-dimensional world is where we are, and then the wave function guides the particle, and the wave function is depending on the configuration space. That seems to be a very clear picture that emerges, if I may say, from your lecture.
Yeah, okay, well, that's a point of view. Of course, there are others. This is a hot topic, if you like, at the moment in Bohm theory about the reality of the wave function and where it lives. Does it live in configuration space, or is the reality the particles? I mean, it's very nice to be able to think that, yeah, the reality is where we are, you know, it's the tables and chairs and all that. That feels very natural.
There's no argument against that. In fact, your pictures show that all the arguments that have been given against that are non sequitur, because Bohm, I mean, you make it very concrete. You have had the merit of putting Bohm back on track, so to speak, in the old days, where he was sort of working in different direction with Heide because he didn't like his 52 theory. And so you have revived the 52 theory, and the 52 theory is really the solution as far as I can tell.
Yeah, well, I'm sympathetic to what you say. I haven't made my mind up about this, and I'm not a strong adherent of you know, reality of configuration space wave functions. It just looks like that to me when you do it. It just looks more natural in the configuration space. You don't need non-local interactions and all that. It just all happens in configuration space. But it's obviously a topic of yeah, some debate.
Okay, thank you very much for your talk anyway.
Well, thank you, Sean.
Well, and
it's so it's just the initial position in the wave packet as it enters the Stern-Gerlach apparatus. I think Jean also showed some pictures of that during his talk. So if it's on the right, it goes to the right packet. If it's on the left of the packet, it goes to the left packet. Yeah.
Okay. Yeah, that's what I thought. Thank you.
Yeah, okay, thanks.
Okay, I think that's it. So thank you so much, Chris, for the opportunity to have your talk. So we really appreciate that. Really, thank you.
Oh, thank you.
So let's just. And just a moment, Bill will say some few words.
Okay, well, what I'd hoped to do was to open this up at the very end to kind of a broader discussion. We can still do that, although we're a bit behind schedule, and we've had a lot of that already. But before we do that, Chris, I just have to say, what a graceful conclusion to this whole workshop. Your presentation and the final slide, it's just like perfect, smooth landing. So that was like a perfectly executed quantum trajectory. Thank you for that.
Well, thank you.
So, all right, totally open. Does anyone have any final thoughts or comments about anything?
Okay, so I have a question. I think it's to all of you. So what do you do with formulations of quantum mechanics that do not rely on Hilbert space? Like, for instance, algebraic quantum statistical mechanics. You have a C-star algebra, and of course you can represent your algebra on Hilbert space, but this is not fundamental, and it's state dependent and so on. So how do you understand this kind of formulations, and can you, you maintain this Bohmian approach in face of these different formulations of quantum mechanics, or I think that's the question.
Does anyone have a response?
Well, if I could just say that was exactly what Haile was working on in the last years. He would say, if he had just listened to my talk, he would say, in fact, he has said to me, there's no such thing as a wave function. You don't need wave functions. What we need are these fundamental processes which are described through various algebras, and these are not in space and time, and somehow space and time is supposed to emerge from these. I never followed Basil down that path because it's very hard to get a handle on it, as to what it's telling us about the world. But there, obviously, Haile was using algebras as a description of the fundamental processes in quantum mechanics, and he was actually able to show that quantum mechanics would emerge from this, particularly the quantum potential and the Bohm theory version. Yeah, so that's another approach.
Just if I'm at the Bohmian, I will say forget all algebras. Bohmian tell me there are Bohmian positions of all my molecules in the shape of me, explain my experience. I don't need any operators, nothing else, only Bohmian position and Hamiltonian. I need nothing else.
To that, I would actually say if you look at quantum systems as they're actually used, say n-body Coulomb Hamiltonian, your observables do not actually form an algebra. And the reason is that they are generally unbounded. So you get a problem with the domains. So yeah, I'm aware there are some approaches where you try to handle that unboundedness, but yeah, we should be making sure that we actually talk about the same thing.
Okay, any other final thoughts, or are we ready for lunch at this point? I think we're ready for lunch. Thank you all for coming. I think it was a great meeting, and I'm really glad everybody could make it both virtually and in person.